So hello everyone. I am Jay, and I am currently an AI resident at AI for Bharat, which is a research lab under Indian Institute of Technology, Madras. Previously, I was a research intern at UCSD, and so far I have worked on federated learning, efficient deep learning, and multilingual NLP. And recently, I'm exploring more multilingual NLP, like language modeling, translation, and data upload. Yeah.
Thank you.
So that's about me.
Yeah, Pranjal.
Hello everyone, I am Pranjal Chittai. I am a MS student in the Department of Computer Science and Engineering at IIT Madras. I am working in the AI for Bharat lab. So before joining IIT Madras, I completed my bachelor's from University of Mumbai in computer engineering. So my research interests are around multilingual NLP, so particularly multilingual machine translation and language modeling. And I have also partially explored efficient deep. This is broadly.
Yeah, so my name is Raj, and I'm currently a researcher at NICT Japan, but I'm also a visiting researcher at AI for Bharat in IIT Madras. I got my PhD from Kyoto University and my master's from IIT Bombay. And regarding my research interests, I work mainly in multilingual natural language processing to focus on machine translation. Document level translation is one of the niche topics that I focus on. I also like efficiency, so I focus a lot on knowledge distillation, grooming, compression, and also recently, obviously, as everyone else is, on pre-training large language models and supervised finding. Okay, so this is how the talk is going to go. We'll have a quick introduction and then immediately jump into prominent multilingual machine translation. We'll talk about data and benchmark creation. Then we'll get into actual focus on relatedness, where we'll be talking about topics on how to enhance relatedness between languages. Then we'll cover vocabulary. We'll have a break. The break is supposed to be for 30 minutes, but we can cut that short to 15 minutes because we have a lot of things to talk about. And during that time, we can have a quick Q&A, so you can get coffee, you can ask us questions. We'll jump into architecture and training, then evaluation, future work, and then final Q&A. So there'll be a lot of densely packed content, so please bear with me. Do feel free to stop us if there are any questions. With that, let's get into it. Jay, you can take over, you can present.
Yeah. So I don't have permission for sharing the screen.
How can you give this? 1 second.
Meeting was can change.
1 second.
Okay, I got it. I hope the screen is visible.
Yes, it's visible. Just go into.
Yeah, I'll just continue to slides. Okay, yeah. So now to begin with, right? Like at least recently we have seen that there's like tremendous progress on LLMs, right? And it seems that maybe MT is more of a solved task, or at least we have reached some, let's say, state-of-the-art systems and like a score of line 70 or something, right? On like some metrics, and it seems like more of a solved problem. So why we should still care about MT, right? In current era, like given that like a lot of focus on LLMs, right? So there are two reasons. So one is inclusivity and accessibility. So for example, if we look at the current MT models as well, right? There is still like a significant gap between low resource and high resource performance. So how can we first like bring that to parity? And next is also like currently we are just scratching the surface, and like there's a lot more to cover. So legacy in terms of the language coverage. So for example, more best MT systems which are commercial cover 1,000 languages out of 7,000. And in open source, the number is still more like far behind. Apart from that, if you improve MT, right, you also benefit across other, let's say, axes as well. So for example, where MT can be used as a data augmentation engine for like improving your multilingual models. So basically you can just generate data using translation, English, like use English data and generate translate data and train a model, like, so you get benefits of transfer learning. And also you can unlock multilingual capabilities on English LLMs as well, right? Using translate and test paradigm. So now let's take a look at how machine translation has evolved over time. So earlier it started with rule-based MT between 1950 and 1980. Then it focused on example-based machine translation from 1980 to 1990, then followed by statistical machine translation between 1990 to 2015. And now post 2015, there has been works on neural machine translation. And as a part of this tutorial, we'll mostly focus on neural machine translation and language relatedness. So how can we build SOTA systems and what are the key considerations and design choices for the same? So now before we jump into the actual, let's say, details, right, about how to build the systems, let's recap some of the basics. So one of the basic building block, right, for any NMT systems that you will see is more like an encoder-decoder paradigm. So where you have a encoder and decoder, basically where, let's say, encoder reads the source sentence and generates a final encoder state. And that encoder state is used as an initial decoder starting state for a decoder, and decoder generates the tokens, right? And this is the standard paradigm that we'll observe across a bunch of works that we'll see like today as well. And now encoder decoder with attention. So it improves the existing systems by adding a dynamic mapping. So basically like which tokens to pay attention to while you're generating at each time step. So that's something like which increase, like let's say improves your context awareness like while decoding at each time step. And for this, you learn attention function. So the attention function basically like checks how relevant a particular token on the source side is with respect to the current time step that you are decoding, right? And it's usually the simplest approach is just taking the dot product, right? So that's the one which was proposed in Bardno attention. And now, like all these approaches are with RNNs and LSTM based networks, right? So one of the like there are multiple drawbacks of this network. So one being they are sequential in nature, which means like we cannot like train them in parallel. And also there's a problem of vanishing gradients, right? As your context keeps on increasing, the amount of updates that you get right at the earlier tokens are like much lower in this ratio of vanishing gradient. So then there was this new architecture proposed known as transformer. And the idea in this case is very similar to the attention that we saw before, but it treats everything as a set, right? And you can just generate a contextualized representation using self-attention. So the self-attention concept here is like given a token, how much I need to attend to other tokens in the context. And based on that, relevance factor, right? You just generate a contextualized representation for each time step. And then you have a multi-head self-attention, which is replicating n self-attention modules. The idea in this case is each attention head captures a different property or at least different semantic meaning. And you have a feed-forward layer post-back. So in the decoder side, it's the same architecture as encoder, but with slight variations. So where first variation is that you have a causal mask where the tokens can only attend to the previous time step and not to the future. And also you have a multi-head cross attention where you use the encoder representations as a key and value and the decoder representation as a query. And you train the network jointly in this. Now let's take a look at tokenization. So tokenization is the basic step of like, let's say given any input text, right? You will break it into like smaller subatomic units, which model can utilize and then basically, let's say, forward, do a forward pass and like basically do the prediction, right? So the simplest approaches for tokenization would be the word level tokenization, where you just simply split the text on white space. But drawbacks of this approach is that it cannot handle out of vocabulary cases. So for example, if you're during the test time, right, if you observed any token which was not a part of the training corpora, then it will just add an unknown token. And also it can result in very large vocabulary with redundancies. So you can see that they're singing the same words with like different variations, right? So for example, head and heads, right, will be two representations rather than legacy. So this adds a lot of redundancy as well, right, for like the case. Next approach is character level tokenization, where you split the text at characters. And one of the advantage of splitting at characters is that you can ensure that the coverage is, you have 100% vocabulary coverage. So which means there would be no out of vocabulary words. And also the vocabulary would be smaller as well. But the drawbacks are if you split it at character, right, it can lead to very longer sequences. And also it might not preserve the meaning which would have been possible at word level, right? So that's some like it lacks semantic meaning. So the best approach would have been like a intermediate solution, right, which uses a hybrid approach, combining word level tokenization as well as character level tokenization. So here the idea is that like the rare words, right, which would be represented at just the character level are the part of vocabulary. And also at word level, only frequent words would be added. So you get best of both, right? And you can then have, let's say, a very well learned vocabulary, which will have like enough good coverage. And now let's take a look at how, let's say, this subword based vocabulary is learned. So for example, consider this toy example where we have following words low, lower, newest, and wildest, and its corresponding frequency of occurrence. So the first step is you just include all the characters that are part of the training data. And then once you have the characters, you do the merge operations, where the idea is you merge the tokens and then take the token like new subword which has the highest frequency. So in this case, we see that E and S gets merged to form ES. Similarly, then after that, we do ES and T. After that, we do LO. After that, we do LOW. And this is how you have the vocabulary learned. And in this case, like you can basically add a threshold, like let's say if you reach a particular vocabulary size, you can exit out, or maybe after n operations, you can just exit out. Yeah. So these are the basics in subword, but there have been some more advanced approaches in subword level NMT. And let's take a look at each of them. So first one would be byte level BP. So here the idea is that we want to, let's say, include all the Unicode characters, right? That might be there in the particular language of interest. But the problem with this would be, right, that it would increase the base vocabulary. So a better approach would be here to use 256 base tokens and then perform merge operations on top of it so that we can ensure that every token is covered. And GPT-2 also uses a byte-based BP vocabulary with 256 tokens and 50K merges. The next approach is wordpiece, where the idea is it was first proposed by Spitzker et al., but it was adopted by Bert and became popular through that. So here in this case, you start with a character level vocabulary similar to BP, but now the heuristics for adding the tokens is that instead of considering just the most frequent word, I add the token which increases the likelihood of the training data to the vocabulary. And then we also have a sentence-based tokenization approach, which is a unigram based. So here also it's similar idea as wordpiece, but done in a bit different way. So you initially start with a very large vocabulary and then gradually prune the tokens, maximizing the training likelihood and minimizing the loss increase. And basically, let's say you do this across until you reach the desired vocabulary size. And in this case, you ensure that at least you have a basic like 256 base token coverage. And here, one thing to notice that there can be different ways of segmenting the tokens, right? Different rules. And the default rule would be like the one which would be most likely, like which maximizes the likelihood. So at least we have so far just recap some of the basics, right, about language modeling as well as neural MT, right? Now let's take a look on how like what different systems were there so far for massive multilingual NMT, right? So first one is Google's multilingual NMT. So before this particular work, most of the approaches which focus on NMT were bilingual models. So this was the first approach which trained a single encoder-decoder based multilingual model that supported translation in more than one language. And this model had a shared vocabulary and also used target language tags in the input sequence to indicate the translation direction. And the authors of the paper show that this approach is data and compute efficient compared to training bilingual models. And as you incorporate more languages, right? So as a result of transfer learning as well, right? You improve performance on low resource and also enable zero-shot translation as well. The next line of work which extends the previous work was Google's massively multilingual NMT. So here the authors try to address the central question of how can we scale these models And as a result for that, like they do two experiments. So first is they train a base transformer model on 59 low resource languages. And in this case, they observe that whenever you are translating into non-English, translating to non-English directions, right? One-to-many models are generally better than many-to-one models. This is because you have a overrepresentation of English data on the target side. But when you're doing the vice versa, right, that is translating to English, right? During that, many-to-one models perform worse than the many-to-many models. And this is because you have a relatively lower representation of English. Although nowadays, like there have been some other approaches to bridge the gap, which we'll look later on in the tutorial. And the next experiment they tried was training a large transformer model where they incorporate 103 languages, 100 and more than 100 languages, and they find that many-to-one models and one-to-many models are better than many-to-many models. And one of the general findings that was from the paper was that N-way corpora is detrimental for many-to-one performance. One way to think would be that let's say when you are decoding on target side, right? If you have N-way data, then your target side would have less diversity. And as a result, there might be some saturation in terms of the translation variations as well as the quality. Yeah. So that is one reason probably for why N-way corpora is detrimental. The another observation that was found in the paper, as you keep on adding more languages, your supervised empty quality degrades, but you still benefit like on zero-shot performance. So the table here shows the performance of many-to-one models compared to many-to-many models on the different languages. And we can clearly see that many-to-one models are better than many-to-many models. And also on the right side, if we look at the graph where it shows a zero-shot Russian translation. And in this case, they consider Ukrainian and Russian. So both of these are relatively similar languages, where they use Ukrainian language in the training mix and Russian do not include any Russian language. And we can clearly see, as you keep on adding more languages, the performance of zero-shot play language, that is Russian, in this case, seems to increase. Apart from that, another work which again tries to push this limit was Google's massively multilingual NMT model in the wild. So here the authors try to particularly address the central question, given a parameter budget, how much can I push the model performance to support more number of language pairs? And in this case, they try out a temperature-based data sampling mix to circumvent the issue of negative transfer between different languages. And also this was the first work to train an empty model with a billion plus parameter. And one of the key finding, which was basically demonstrated in the paper, is that quality is directly proportional to data size. So suppose if you are training an empty model, and if you have a like data at higher volumes, then probably you will have like a very good translation quality on those language pairs. And the following plot shows the performance for E to X direction. And left to right, like the data volumes are decreasing. So you start from high resource to low resource. And you can see that as you move towards left, right, the performance of the model tends to decrease. Apart from that, if you look at the figure in the left, you can see different ablations on how the performance of the model varies as you keep on adding different languages, adding more languages. So during the 2019, it was shown that like 25 is the optimal languages that can be added to a billion parameter model. However, this has now like surpassed, and you can add even more in languages when you're like, let's say, dealing with even billion parameter space. But just to give you the context. And on the right side, if you look at the table, you can see that many-to-one models and one-to-many models are better than the many-to-many models as per the numbers on high resource, medium resource, and low resource languages. And now, so most of the work that we saw before, right, those use English-centric data. So which means like they just mine data with E2X data, and then in order to even train the many-to-many model, they just do pivoting where they just find the XY pairs which share the same English text, English sentences. But this was the first, M200 was the first work which trained a model with a non-English centric mined data. And for mining this non-English centric data, the authors released Laser tool, which is a sentence embedding mod, and also FastText for language identification. We'll look into more details of this models like sentence embedding models further in the sections. And this was the first model which supported a total of 2200 language directions, which is a 10x increase in the number of directions supported by the previous best English-centric models. And compared to English-centric models, we observe performance improvements of 10 points with this model, new models. So here is the architecture of the models. So if you look at, they have a shared encoder, and they also have a partially shared decoder and a sparse decoder. So here, the shared decoder are like just initial few layers of the network where, let's say, you learn some very low level representations, and then you route it through the different language specific parameter, language family specific parameter decoder module to basically refine the outputs and actually, let's say, capture the particular context or some of the biases of particular inductive biases that are there for the particular languages. And in this case, we can see an example for Mandarin to French translation where we see language group B parameters are activated basically in the decoder. And now coming to the results, we can clearly see from the table that M200 improves over English-centric models by approximately 10 points. And one more observation is that M200, the best model, which is 15 billion parameter model, leads to an improvement of 1.2 blue point over the base model, 1.2 billion parameter model. Here. Apart from that, the other approaches are more like where you do continue, like let's say some pre-training, and then basically on top of that, like you use that as an initializer and basically do a like training of a translation or like fine tuning. So one such approach is BAR, where the authors adapt the MLM objective, which was originally proposed for encoder-based models to encoder-decoder LMs. And in the figure on the left side, we can see that it's an auto-denoising objective where maybe you just corrupt certain tokens or span in the input, and then the decoder has to correctly predict the denoise output. And there are different denoising schemes which are shown on the right. So it ranges from token masking, sentence permutation, document rotation, and so on. And the original BART model was like English pre-trained model, but later on, I think subsequent works have also been explored in multilingual setting, leading to MBART 25 and MBART 50 as well. And in this case, once you train a BART model using this denoising objective, then you fine-tune the model on specific task of interest. So one such task is like translation, for example, where you just pass the input source text on the encoder and target text on the decoder side and just train it on a supervised objective. Apart from that, so at least nowadays we have a very good pre-trained encoders, right, which have been trained on extensive amount of monolingual data. And at least it seems intuitively that it's a good idea to start like use them as a good initializer and stitch them together and repurpose them, right, for translation tasks. So one such work which explores this is Delta LM. So where they initialize the encoder and decoder of an empty model that they want to train with the pre-trained encoder in XLM. And then they train this initialized model with monolingual data as well as bilingual data using the MLM objective as well as TLM objective. And some key differences compared to like the standard stitching is in this particular work is that they use internal decoder, which means that they use fewer decoders than the encoder layers. So in this case, they use 2/3 of encoder decoders. And also one more thing is rather than using the vanilla decoder, right, where it's self-attention, cross-attention, and feed-forward, the authors introduce a feed-forward network between self-attention and cross-attention in this case. And for initializing the parameters on the decoder side, authors use odd layers for initializing the parameters of self-attention and first feed-forward network, whereas the cross-attention and the upper feed-forward network is initialized by the even layers. And now the table shows the performance of delta LM on different language directions, and all these are blue scores. We can clearly see that delta LM models, yet being compact and smaller compared to other models, can outperform like much bigger models like M200, which is of 1.2 billion parameters. So at least this approach is promising, and repurposing existing models and stitching them together is a much better way rather than just starting from scratch. Another line of work which was released last year was NLLB 200. So there is no language left behind. So this was the first open source model to support 200 languages, and it included lots of low resource languages as well. The authors made contribution across different fronts, starting from data collection to model building as well as evaluations. So in terms of the data set, right, like when you want to curate the data, there are following considerations. So like language identification, monolingual pipeline, and laser, basically like a sentence embedding model that you would use. So for language identification, they train a LID 200, which can identify text in 200 languages. Then for monolingual pipeline, there is a Stokes library, which you can use to do large-scale data mining. And laser 3 is used as a component within Stokes to actually do mining. And for mod, they have two variants. So one is a sparse variant like MOs, and the others are dense models. And also they distill like the MOs and dense variants to a much smaller like compact models as well. Apart from that, in terms of curriculum learning, they show that like introducing low resource at later stages is better, and you should first just train with high resource language to prevent overfitting. And also they show improved low resource BT, which means like a better, let's say, strategy for collecting diverse BT data include from existing SMT and multilingual models. And which improves the low resource, let's say, BT as well. And they also do world level distillation. And also for the human evaluation, they use XSTS guidelines. We'll see this more details in the subsequent sessions. So now, if you want to, let's say, so what would be a standard recipe, right? If you want to like maybe train a model which can, let's say, scale up to 200 languages, right? So one is a mixture of experts, because here in this case, the model supports more than 200 languages. So essentially the data volume is like comparatively much higher. And mixture of experts are a very good way to handle those, and also kind of, let's say, exploit the data patterns, right, which are there, and improve like performance across different languages. So maybe you can get better sharing by routing low resource through, let's say, shared weights. Next, it can also prevent overfitting on low resource, because if you look at mixture of experts, it's a bit more sparse model, right? Where only few experts are activated rather than basically passing through all the experts, right? So that's like low chance of overfitting as well. Next thing is curriculum learning, where you train first on high resource and then basically gradually introduce low resource to prevent overfitting on low resource. And also do supervised learning, self-supervised learning, where you use monolingual data of low resource or linguistically similar high resource language to enable cross-lingual transfer, and then use that initialized model to start the train on NMT. And also diversified back translation using different combinations to increase the data diversity. Yeah. So now if we look at the different metrics or like blue score for, let's say, different variants of the models, we can clearly see that from left to right, the models tend to increase. The baseline is a 3.3 billion transformer model. SSL is the baseline model, but also like jointly trained with SSL objective. And BT is the baseline model, like trained all jointly with the back translated data. And NLLB 200 is a 54 billion MOE model. We can see that when we go from left to right, each strategy improves the performance of the model, and MOE models tend to like outperform the baseline by approximately 3 to 4 points. And these are like scores on Flores 200 benchmark, which is English-centric performance theories, for example. Now, another line of work which was recently proposed was MATLAB 400, where here the authors propose a rigorous filtering scheme for filtering out, like removing noisy data from Common Crawl across 400 languages, and this resulted in a monolingual data of 3 trillion tokens. And they do a joint training where they do mass sequence denoising and cross entropy, that is a standard translation objective, to train 3 encoder-decoder variants ranging from 3 billion to 7 billion, 11 billion. And also they train a decoder on the LM with UL2 objective just on monolingual data. So for encoder-decoder models, they also utilize the empty data as well. And this is the following table result shows how the models perform compared to the NLL. We can clearly see from the table that MATLAB models like are performing on par or at least like competitive with the NLLB models, like get covering more than 400 languages, which compared to NLLB was just 200. And also on the right side, we can see that for LM, when you just have a decoder only model, which is not trained on any empty data, as your shots increase, the model performance tends to improve gradually. And now, so we so far saw that like most of the approaches have been just for 400 languages, right? At least in the open source literature, it's been. And now there are some of the approaches which, at least for commercial systems such as Google Translate and so on, where they have actually tried to even scale this to more than uh, like around 1,000 languages as well. And the key idea of that particular approach is you use monolingual data as well as parallel data from high resource languages and leverage self-supervised learning and basically supervised objectives to enable transfers to low resource languages. And in this case, they do a single stage joint training with denoising and translation, and they get a good performance, like at least across different languages, and good zero-shot performance as well. So some of the findings on the particular work are that high quality data improves the performance on related zero resource pairs as well. And when making a decision about whether to, like, let's say scale on parallel data as opposed to scaling monolingual data, one should like focus more on scaling parallel data uh, because that's more of a supervised objective that the models are trained. And also adding this self-supervised pre-training objective makes the model more robust, improves the domain robustness of empty models. And single stage joint training is better than two stage training strategies like BART, where you just train the model, like first do a pre-training and then post that you do a transition based TLM training, finding. Yeah. So far we saw that most of the works that we saw, right, are just focusing on like building out massively multilingual models, right? Like basically using one fit for all approach, right? But there have been some subsequent works in parallel which focuses on developing this language family specific models where like there are different, let's say, language family specific properties exploited in order to improve the performance. And like by using these properties, you can get much more smaller models as well. Correct. Yeah. So we can see that the different color regions highlighted in the map like indicates the different language family specific models like out from the particular regions. For example, in North America and South America, we can see indigenous DeFi and indigenous BART models. Similarly, for Africa, we see AfroBART, AfroLM, MMT Africa. For North Africa and Middle East, we see Madar, Arabert, and Noor. For European languages, we see Opus MT and M4D2. And for Indian languages, we see Indic BART, Indic BERT, Indic Trans. For Southeast Asian countries, we see Indonesian BART, Indonesian GPT, Thai BART, and SC Translate. And similarly for Chinese languages as well, we see Chinese BERT and Chinese DeFi. So we'll be covering more details on what sort of related properties we can exploit further to build this smaller compact models like leveraging language relatedness and also compete like with this bigger models like which are using just one fit for all solution in the subsequent sections. Yeah, so I'll probably now ask Ranjan to continue. Please not sharing.
The screen is visible, right?
Yes, it is.
Yeah.
Sir, if
So-
you can turn on the video, would be nice.
Yeah. Yeah, is the video visible?
Yeah, it's okay. Yeah, please continue.
Yeah. So let's just start by discussing the main considerations for building state-of-the-art models. So the So the first aspect is data. So for training any machine translation model, so you saw some previous state-of-the-art machine translation model systems. So the principal component in all of those was data. So you need, as they say, garbage in, garbage out. So you need data which is of highest quality to ensure that your model actually performs well. You also need data that is multi-domain and representative of content from different varieties of styles of text and different types of content to ensure that it is robust across a set of domains and not specific to a certain domain. And you need to ensure that it is not toxic. So you need some quality control filters on the data front. And the next aspect is modeling. So under modeling, you'll have to make choices as to what sort of architecture to choose, what sort of pre-training strategies or training strategies, what sort of properties can we use to improve sharing and transfer learning between related languages. So these aspects come under modeling. And the final aspect is benchmark. So given that we train some model, we need to understand how good it is, and we need a holistic sense of how it is performing and what more can be done, what are the errors or shortcomings of the current models, and then we'll try to get a understanding as to how to improve it even further. So the standard recipe for training any sort of deep learning model has uh, implies that you have to work across all these three axes. Now let's just dive deep into some of the findings from previous works for the task of neural machine translation. Yeah. So for neural machine translation, you need high quality data. So the data here is parallel corpora, byte text data. You need that to be of highest quality. You need domain diversity in the data. So usually data for training empty models is from mine corpora, but that might not be sufficient to cover a large set of domains. Or if you want some niche domains, you'll additionally need to curate some additional data, which we'll talk about later. And on the data front, some language relatedness techniques can also be applied to improve the performance on low resource languages. So some examples might be script unification or source pre-ordering. These will be covered in the respective sections. So in terms of modeling, deeper architectures are known to be better than wider architecture. So use deeper models. Training objectives. So denoising plus empty objective has been shown to be better than doing a two-stage approach. And in terms of language relatedness, some sort of parameter sharing to or forcing the representations between related languages to be similar tends to improve performance on lower resource languages. And coming to benchmarks, to get a holistic evaluation, it is important to have multi-domain benchmarks, which are representative of different formality levels. And by formality, I mean formal content as well as informal content. You would want a SOTA model to do well across both the fronts. And generally, benchmarks are limited in nature, and to ensure that the model is suitable for deployment in a particular demographic region, we would need a benchmark to be representative of content from that specific demographic region. So we'll talk about a details of these in the respective section. So let's start by jumping into data. So for training machine translation models, you need parallel corpora. So the parallel corpora can either be mined from the web or it can be human generated. So firstly, mine data is at larger scales. Creating human data at those sort of scales is nearly impossible due to the operational costs. So let's just first start by understanding how to mine parallel byte text data at scale. So for mining parallel byte text data, the first thing which you need is monolingual data. Monolingual data is abundant on the internet. You have a lot of websites and many websites are in multilingual formats. They offer the same content in more than one language, and particularly these regional language websites are a very good source of getting parallel corpora. Just that we need to understand how to align sentences from these parallel websites. Other sources might be books, but mining data from so curating this monolingual data from books might not be so straightforward, because books are usually difficult to crawl and need sophisticated text extraction techniques like OCR or so, and so it might not be something straightforward to do, or would need some human intervention as well. So usually data from websites is what is preferred, and web data has been crucial for, as we see, web data has been crucial for training language models, as well as for bytetext mining for training translation models. One such example of a large-scale web crawling effort is C4, which was then subsequently expanded to a more multilingual setup, and the MC4 corpora was created. So let's just understand workflow of how monolingual data is curated. So first step is to get a list of URLs, and then these URLs are filtered to remove offensive or copyrighted content or spam content. This might involve a human in the loop, or some automated ways can also be created for this. Once the URLs are filtered, from those URLs, we have to extract the content. So for that, we have several tools like Boilerpipe, Varshare, Trafilatura. Once the content has been extracted, you would want the text to be in the same language that you desire. So we need a language identification pipe in the pipeline. Language identification can be done using script-based methods or model-based methods. So model-based methods might be a bit slower, and given that you're dealing with large-scale text, a better approach might be just eliminate script-based. So if the script is not seen, just eliminate those, and then post that you apply model-based methods for much fine-grained analysis and ensuring that the quality is you get the utmost quality out. And now that you have identified that the text is in the right language, and you filter out the documents for a particular language, now you don't need repetition or toxic content on a document level. So you apply a in-document repetition removal and toxicity filters at the document level to eliminate such documents which you don't desire, or you don't want such biases to creep into your systems. So post this document level filtering, we apply a line-wise filtering to remove undesirable lines. So or some advertisement or some sort of non-textual content might also be a part of the web crawl. So we'll need some heuristics to remove such undesirable cases and just retain good quality sentences. And we apply these sort of heuristics to get to a sentence level, and then post which deduplication is applied. Deduplication can be fuzzy as well, or exact deduplication. At larger scales, usually fuzzy deduplication is what is preferred, and exact might not be possible to do. So this is a broad workflow of how monolingual data is curated. Yeah. So let's just discuss few large-scale monolingual data curation efforts. So basically, you can categorize data curation efforts into two subgroups. One is large-scale, and some of them are language group focused. Large-scale examples of large-scale are C4, which is for English, then a multilingual version of C4, Pile, Red Pajama, Refined. The main consideration for large-scale efforts is usually they tend to apply a one-fit-all heuristics, and they do not add any fine-grained or language-specific details or heuristics, or maybe some particular LID model might be good for a specific set of language, but they try to have a unified approach or one-fit-all approach, and conducting what might be good for what sort of languages is not possible given the scale at they operate. So they usually tend to work with a one-fit-all heuristics, and this approach might result noisy corpora at scale for a language. So you'll definitely get the scale of the data you get would be much higher, but the data might not be of the utmost quality and might have some noise due to a one-fit-all heuristic being used. So another alternate approach is language group focused monolingual data curation effort. So these also run in parallel. So for Indic languages, we have Indic Corp V1, V2, Varta. Indonesian languages, we have Indo Energy. For indigenous languages in Corpus, there has also been subsequent similar efforts in the African language setting, where WebCrawl African language corpora was released similarly for Creoles as well. The advantage here is that given that you are operating at a small language, you could calibrate your heuristics or settings to so in the pipeline which we discussed earlier, you could have much more fine-grained heuristics to ensure that the data I get for these languages is of the utmost quality. And these two are not independent. So findings from language group focused efforts can also be used to improve the next large-scale crawling effort. So these two are supportive to each other, and both are equally essential to progress and get more high-quality monolingual data. Yeah, so now that we have monolingual data, now the second stage is to align the monolingual data. So let's say I have a large scale collection of monolingual data for English and a large scale monolingual data collection for French. I would need some model to represent these sentences from each of them to a shared multilingual space, and then I'll do a nearest neighbor retrieval on that. So now we discuss what sort of sentence embedding models exist. So the first model which we'll be discussing is LAPSE, a language agnostic word sentence embedding. So it is a dual encoder approach for training. So you have two encoders. One is for embedding source text as well as target text. Note that both of these are shared. The parameters are shared, and both have been initialized by pre-trained multilingual word. And one approach might be, so first question you would ask is whether we can apply some sort of MSE, but no, because this is an encoder only model, and it might lead to representation collapse if you directly apply MSE based loss here. So what is done is a contrast to a loss. So you do a translation ranking. So the actual pair should be ranked higher than the non-actual, so the other pairs in the batch. So you do the other sentences in the batch act as your negative samples, and you want the correct sample to be ranked higher, and you want so to ensure even go even for a step further, you would want the actual pair to be separated by a margin from the negative sample. So this is much similar to SVA, the principle of SVM. You should discriminate good and bad pairs. So this is how the model is trained. And firstly, after initialization, they do a continual pre-training followed by this translation ranking task. So this LAPSE model is like a one for all approach. So it is like a single encoder model which supports 109 plus languages. Similarly, there has also been parallel efforts like laser. So laser is like a encoder decoder model. Previously, LAPSE was an encoder only model. So for training laser, they use an encoder decoder setup, and so they apply max pooling on the encoder output to get a fixed size representation, and that is then added to during the decoding stage, that is concatenated with the sentence embedding and then passed to the decoder. So here they use the NMT objective for training, and they use byte text data to align multilingual representations. Yeah, so Laser 1 supports 93 languages, and Laser 3 used a BiLSTM based encoder decoder, and the training objective was NMT. And subsequently, this was a newer version of laser model. So they just use SPM instead of BP, as we had already discussed the differences between the two. And for constructing this, they had a better sampling of better distribution where the low resource languages were upsampled. So this leads to better. So we'll discuss more about these in the vocabulary part when we reach there. And so post this, the authors for laser 2, the authors describe that a unified approach, that is a single encoder for all the languages, may not be the optimal way of doing things, as low resource language. So there might be a negative impact on low resource languages due to unrelated languages being a single encoder for all languages might have some negative interferences between unrelated languages. So what they propose is distillation of this newly trained laser 2 model into language specific encoder, language or language family specific encoder. So let's discuss the distillation. So what they do is teacher student approach, where laser 2 acts as the teacher model, which representing which where you pass in English text, and the student model of the particular language or language family is uses text from the so you use pipe text data to align, and as well as monolingual data, a combination of MLM as well as distillation loss. So they use cosine loss for between the embeddings of the teacher as well as the student model, and the model which was thus obtained from distillation. So they have distilled laser to into 147 language or language family specific encoders, and this in total support 205 languages. And this laser 3 model was observed to be on par with LAPSE, as well as they extended it to more low resource languages by incorporating monolingual data of low resource language during this combination of distillation and MLM. So they say that this language specific encoder approach might be good approach for particularly for low resource languages. And subsequently, there has also been a follow-up work where it is exactly the same as laser 3 distillation. They just that they use contrastive loss instead of cosine loss, and the results say that this laser 3 trained with a contrastive objective outperforms the original laser 3 model. Now, recently, a newer approach has also been proposed. This is multilingual sentence representations music. So the setup, if you see, this is very much identical to the laser setup. Just that the laser setup involved bilisting. Here we just replace that with a transformer model. Pretty much identical. You max pool to get a fixed size representation, then add. Then concatenate at each decoding step. You just concatenate this, and this is the overall setup. The data which was used to train, in case of user, there are no language tags added. This is because they train any to English model. So XEN model is what they train. So they don't need explicit language tag because the target language is always English. So what they do is a two-stage training. So first stage involves pre-training. So stage can be thought of pre-training, where they train on the NMT objective using the above model architecture. And once this model is trained, they impose an additional loss function. So this is the cross-lingual consistency loss. So what they intend to do is so you get so for an input you obtain, so for Chinese input you obtain output distribution for English, and for given in English as input, you also obtain an output distribution for English. So as this model is a XEN model, it would have tendency to output English even if it is given English. So this is similar to auto encoding. And what you essentially do is apply a KL divergence between the two and then backpropagate. So this sort of implicitly force, as you are constraining the outputs to be similar, this intrinsically makes the encoder representations closer to each other for so if the pairs are related, their embedding encoder representations are related, and they train it in an English centric manner such that all of the languages align, if they're parallel, they get aligned to each other. And the results say that Muser model outperforms all the previous existing techniques, and this is better than laser 3 or LAPSE, which were the previous best techniques. And their evaluation is on this is the retrieval accuracy for X2 EN. So retrieving an EN sentence for Flores 200 given an X sentence. So and their numbers say that this Muser based approach has outperformed the previous. Recently, there has also been a newer embedding model. So this is like a multimodal model. So you can use it for aligning speech as well as speech text as well as text. So let's briefly discuss how this is trained. So firstly, you initialize first you train the text part of it, and then you just use this as the teacher model, and then align the speech encoder to the text encoder. So firstly, the text encoder is initialized with the NLLP model, a 1 billion model, which is like a machine translator, which has been already trained using a machine translation objective. And note that here there is no cross attention as we previously discussed. So this setup is exactly identical as the laser setup. But additionally, so laser just use the machine translation objective. Here they use a multiple combination of multiple objectives to improve the sentence representation. So they use auto encoding along with machine translation. And additionally, they apply a MSE between X and Y, where X and Y is a byte text pair. So they apply a MSE loss between the two embeddings. Note that here applying MSE would be feasible because additionally you also have a auto encoding, denoising auto encoding task. So there would not be any representation collapse because you would impose a constraint for the embeddings to be close to each other, but not fall to the same point because you need to reconstruct the original sentence back from it as so this sort of combination of losses works well is what they propose. And once your text encoder has been trained, what they essentially do is they freeze the text encoder and use transcription data to align the speech encoder to the text encoder. And this is how they use a teacher-student approach. This is identical to how laser 3 distillation was done, just that here we are aligning two modalities using transcription data. And if you compare the results, we can see that this sonar embedding model is better in terms of retrieval, so has better retrieval performance than the previous best. So LAPSE or laser 3, this is much more better than the so XM is like a retrieval error rate, you can say. There we won't go into too much specifics, but a lower XM indicates that the embedding model is much better. So the sonar embedding model is much better than the existing LAPSE or laser 3 based. So after this detour, let's just go back to our original problem. So given that we have data at scale, so the reason why we expect to get byte text from these monolingual crawls is because the same website might be present in different languages. So there is a chance of getting parallel matches for the same set. So what we essentially want to do is you have a shared multilingual vector space. The model can be LAPSE or laser or any embedding model of your choice. You represent the sentence from English and then you represent all the English sentences. Now given a sentence from, let's say, a newer language, say I want to retrieve nearest neighbors from English for the sentence in Swahili. So I just take the sentence in Swahili, embed it using the same sentence embedding model, and then retrieve the nearest neighbors from the English space of English models. Note that here, if your monolingual corpora are of much larger scale, then this is not possible to do because that would just eventually mean you need to conduct a brute force search of X cross Y, which might not be feasible due to computational constraint. So in a way, how to do this efficiently. So there is a library called Facebook AI Semantic Search, FAIRS. So they use efficient representation so they do efficient indexing and then it is which is based on clustering. So now using FAIRS, it is much easier to conduct this semantic matching and retrieval. So you could reach a throughput of 1,000 sentences retrieving 1,000 sentences per second. So this is much efficient to do if you use FAIRS. So what we are discussing is the CC matrix style of doing things. So this is like a global match. So you take all the monolingual sentences in one language, you take all the monolingual sentences in the other language, and then conduct a global search and then mine the parallel pairs from large scale corpora. But note that this has very high computational cost, but the process is completely automated. There is no need for any manual intervention or manual heuristics identification. So you use FAIRS index for efficient indexing and retrieval. This approach of conducting large-scale mining yields you large-scale data. However, the quality might be compromised because there is a chance of false positives as well, because you are comparing everything against everything. So, and our sentence embedding models might not be perfect, and there might be some partial matches as well. So, a sentence. Few sentence opposite in polarity or of a different context might be mined as a parallel pair by these sentence embedding models. But the reason why this is happening is because we are comparing everything against everything. So this sort of approach maximizes recall, but there might be a compromise on precision. So this sort of approach is used to get data at scale, and the data might be noisy as. So a question which we would ask is, can we do something better? Yes, we can do something better, but the problem is that you'll get data at much lower scales, and you would need some heuristic based. So if you know that two documents, let's say I have some sort of data which I know that this document in, say, X language is aligned to that document in Y language, then my search space is just reduced to a document level search instead of conducting a full scale search across all the monolingual corpora. So but identifying this document level alignment might involve some human effort, or you need some sort of domain knowledge to identify these aligned sources which have such document aligned data. Here, the advantage is that you only conduct a local search, so there is lesser likelihood of mining false positives. This is much faster and scalable, and you have more chances of mining high quality byte text. You need lesser computational requirements as you are conducting a local search only. And given that you know that the same English, if let's say if a same English document is aligned to multiple documents in multiple languages, then this leveraging this domain knowledge might be very useful resource for mining non-English parallel pairs. So a CC aligned style of mining, the emphasis is more on precision, and you need some sort of human effort to get these document level aligned corpora, and then you can get high quality data and conduct with lower computational costs. So now we have been discussing a lot of sentence embedding models, LAPSE, laser. So a question which anyone would ask is, which model should I use? Yeah.
So sorry to interrupt. We might run out of time on some of the other parts of the tutorial, so you could probably rush through the remaining part and focus more on the important points.
Yeah, sure. So to choose the if you have any sort of semantic textual similarity rated data, human annotated data, so given XY pairs, if you have some human ratings of 6-point annotation between what sort of alignment is there for the text, then you could compare the correlation of these sentence embedding models, and whichever model is much more correlated with human judgment, choose that model as your go-to model. So the second question which you would ask is whether filtering is important. The first in that you'll ask whether noise impacts training. So the answer to it is it depends. If you are operating at very large scales, there have been some previous works which show that data at scale matters, and noise has minimal impacts on the training model training. But if you are operating at lower scale, so in terms of our experimentation, we observed that eliminating noisy data does improve NMT performance. So we directly go to the numbers. So we apply some sort of filtering. We'll discuss what was the filtering used on the next slide. But as we can see, we are just using 1/5 of the data, but our NMT performance is much superior to just using noisy data at scale. So which implies that using high quality data is much more important. And this is also good in terms of training efficiency, because you could converge faster and do away with large scale computational requirements. So our finding was data quality matters over scale when you are working at smaller data and model scales. So for parallel purpose filtering, one way might be to apply cosine similarity thresholds on the embedding model which you use. And for lapse model based on prior studies, 0.8 and even our work shows that 0.80 the threshold is optimal for lapse, and this is language pair agnostic. And there is a catch that these embedding models might vary in performance with terms of sentence length. So additionally also have a heuristic where if the token counts of the two sentences, there is a lot of difference between the token counts of the two sentences, they might not be aligned to each other. So you also additional filter to eliminate these sentences which have a large difference in the token counts. An alternative approach might be use Comet, which is like a reference-less evaluation method, and you just use the reference-less version of that and check the calibration. But the issue with Comet is it is language or language pair dependent and might not be calibrated for your language pairs of interest. And there is no one fit all threshold for Comet. So you'll have to empirically determine what threshold works for your language pair of interest. So you'll need to work more and be cautious of when using Comet. As against Lapse, you could work with a 0.80 threshold, and that might just do the job for you. And these sort of data which we discussed are mined data, and mined data are opportunistically created. So there is no control on the domain or style of text which we are covering. So and particularly these only cover the higher resource languages. And if you want to incorporate low resource languages, there would be a need of creating high quality human annotated data. So this has been around since 2010. So for Indian languages, they'll see initiative created tourism specific data for Indian languages. Recently, there have been several multilingual efforts as well. Covering NLLB seed is like a multi-domain corpora, which is a very rich resource for low resource languages, and massive, which is seed data, human annotated data, which covers spoken content. And in our work as well, we create some India-centric multi-domain data, and this is particularly to focus on inclusion of content, which is typically not covered in web crawls and or informal content as well. And our results indicate that fine-tuning models, so you train on a large-scale web data, and then if you fine-tune these models with limited human annotated data, but that should be multi-domain, you get an additional performance boost of 2 to 3 CHRF points. So having some sort of human annotated multi-domain data is always beneficial to sort of improve your performance even further. Yeah, coming to the benchmarks part. Benchmarks are indicators of performance of systems across different settings, and benchmarks are harder to create and limited in quantity. And most of the benchmarks which are currently available are general purpose. But so performance on those benchmarks might not be reflexive of how models would perform in a real world or production setting. So you need, and I believe that most of we have in NMT we have reached a fair point, and to further improve our performance, we need some multi-domain demography specific benchmarks to identify whether these systems are suitable for deployment in actual real world settings or not, or what sort of issues exist in these systems and how can we further improve them. So creation of benchmarks, demography specific multi-domain benchmarks is imperative to drive further progress in NMT. So, but creation of a benchmark for tasks like NMT is much harder than it seems. The question why? Because there are so many systems out there. So there is a high chance of biases creeping. So you need a strong quality control procedure to eliminate such sort of biases. Coming to existing benchmarks, then let's just have a quick overview of what the existing benchmarks are. WMT has organizes several shared tasks every year. So the benchmarks from the WMT shared tasks are direction specific, human generated, but they lack language coverage. Mostly they are for few languages or a group of languages, and they have limited domain coverage. Mostly WMT has been traditionally news domain only. Recently, Entrex 128 is just a extension of WMT 2019, the benchmark from there to 128 languages. So they improve upon the language coverage, but the issues, the same drawbacks exist here as well. The content is only news and mostly formal or prose style of text. And an alternate benchmark is Flores. Flores is like has the largest language coverage, and has the largest domain coverage if you consider on a macro level. But the issue with Flores is it is from a single source. Most of it, all the data is sourced from Wikimedia entities only, and this has limited demographic coverage. So it does not represent the named entities or style of text which you would encounter in your geographic region, and it has only a certain style of text and might not. So performance in Flores might not guarantee you performance, real world performance in your demographic region. And mostly text in Flores is prose or formal. And recently there has been a lot of usage of NMT in speech-to-speech systems or conversational agents. So we would need some benchmarks to evaluate capabilities of NMT systems to deal with those sort of textual scenarios as. And this is like a wish list to create a new NMT benchmark. You want the benchmark to be multi-domain, covering content which comes from diverse sources. You would want a new benchmark to have demographic coverage of the region which you are targeting. You would want to have formal as well as informal style of text. You would want it to be quality controlled. Quality is paramount. You will need some strong heuristics to ensure that there is no plagiarism and biases from any system. And you would want this benchmark to offer something new. It should not be over representation of an existing benchmark. So you would want want to apply some sort of filtering strategies to eliminate some domain or distributional matches with existing benchmark, so that this when new benchmark which you create offers a fresh perspective and fresh evaluation setup for your language frameworks. So a quick pass over the benchmark creation process. This is like first step is to identify sources of multi-domain content for the set demographics. Then you have a sentence verification stage where you verify the sentences, classify if you want to create a specific distribution of domain or sentence length, then sample accordingly, then get the sentences translated into the desired language, then have some sort of quality control checks. These can be blue score based checks, such that if let's say you know the performance gap between the two systems, and let's say on a set translation reference which has been created by annotator, if the difference between the two systems is much higher, then that indicates that the translation is biased towards a particular system. So you need such automated plagiarism detection mechanisms to counter these, to prevent biases from creeping into your benchmark. Then post these have been automatically validated, you need a final review stage to ensure that the translations are of the utmost quality, and then the benchmark which is created is of the utmost quality. So now that you have training data, you have benchmarks, there is a chance that these crawls which you do, parallel training data is curated from the entire internet, and benchmarks are also created from content on the internet. So there is a chance that there are leaks between the two. So you need to apply strict deduplication techniques with benchmarks to ensure that there is minimal data leakages and ensure that the evaluation which you do is fair enough. So you have pre-hoc deduplication, so where you eliminate data leakages from training data or pre-training data to ensure that your evaluation is fair. Or if it is a newly created benchmark, you only evaluate those sentences where there are no overlaps with the training data to ensure that your evaluation is fair. And a quick overview of the techniques for deduplication. So one might be parallel or exact dedup, where you eliminate XY pair if they're directly present in the benchmark. This is lesser strict. The second one might be monolingual dedup, where you combine all the monolingual side of the benchmarks, and this eliminates paraphrases as well. So if X and Y are not the exact pair, and there are some paraphrases in the training data, those might not be eliminated in the previous stage. But now that in the monolingual dedup setting, you eliminate those as well. And this is exact dedup. And an alternative might be to do a fuzzy dedup, where the matching is based on n-grams and even more stricter. So these are techniques to eliminate leakages from the training data. Yeah.
Okay, we are pretty close to break time. So before I start my section, where will be on modeling, we'll have a quick Q&A. And so yeah, the session is now open for questions. Also, you can feel free, you can have the coffee outside. I think they've already prepared, have some snacks. So while having snacks, you can have questions, anything. Yeah, feel free. Yeah, if you don't have questions now, you can ask questions later on this topic.
I have a question.
Yeah.
I think so. I think at one point you were comparing alignment of sentences with human alignment, right? To understand to measure the quality of different techniques like laser and other such techniques. So I was wondering, are there any test sets that were standard to be using in that process, or how were the human test sets actually getting great for that?
Pranjal, did you get that?
No, I did not clearly get it. So I think
Yeah.
what I go for.
So maybe Raj, can you just repeat the question once? I think I'm
I believe at one point you were comparing, you were evaluating the quality of techniques like lapse and laser 3 by comparing them against like human alignment. Was that something I caught?
Yeah, yeah,
So,
yeah. So
how
go ahead.
started for that, or how did you construct them, or like how is that evaluation? So if you would share some more details of that.
Sorry, could you repeat the last part? What did I say?
That we do a bunch of like the novelty detection,
Yes,
right?
yes.
So how do we know for sure whether the evaluation benchmarks that we've created are definitely novel? Do we know if laser or anything has the ability to capture that we are definitely creating something new over here? Or did we not
Okay, you mean that there is a leakage in the STS data which we create or not? So whether
No.
that has a
No, so I think the question is like whatever new benchmarks that we, let's say, intend to create, right? How can we maybe ensure, let's say, the benchmarks are more novel, like based on like some sentence and medium approaches, right? Is that correct? If I understand the question.
Yeah. Jay, can you speak a bit closer to your mic?
Yeah, so is that the question?
Yeah, that's the question, yes.
Yeah, so I think the problem with the sentence embedding models is, right, like they are also trained on a certain set of data, right? So eventually they also have certain biases, right? So they might not, let's say, accurately reflect the benchmark, or it is a case for which you're constructing the benchmark, right? So I would basically recommend that basically if you are thinking about that, right, rather not like say just stick to one solution, but have like a maybe some other, let's say, heuristics as well. So one way, like let's say, would be the domain or the content type, right, where that you are, let's say, creating. So at least that would be indicative of whether there's any benchmark out there or not available. Apart from that, like the another thing is like to ensure that the data is more novel, or at least like let's say the case, right? You can also think about like the difficulty of the data, right? So maybe like think about some uh, like usual challenges, right, that are there. So maybe like longer sentences or like cases where this models tend to fail, right? So that is one like simple like filter or heuristics that you can apply. Apart from that, like there are other n-gram based approaches as well, right? Like you see that you can just if you just want to avoid like just have a data into one domain. But I would say that although this embedding based models can indicate you like an estimate of quality, but they can also be misleading if, let's say, you're operating at a very niche domain, right, which the models cannot fairly represent.
So I'd also like to add to that, saying that we have dedupe mechanisms, but the problem is if you are comparing against too many things, exact deduplication becomes complicated. So that's where fuzzy deduplication comes in. But fuzzy deduplication means you might miss out on something. So I think there have to be multiple layers of filters to make sure that you have actually novel and distinct data from whatever is existing. And I think that would be the ultimate solution. So that's a work in progress. Even the LLM people have difficulty filtering the benchmarks from their training data. And it's a whole big argument as it is. So I think it's a work in progress. Thanks. Any other questions? Okay, yeah, we'll be able to take questions anytime. So let's take a 10-minute break. Please enjoy the coffee, snacks, and we'll get back. And this is where we'll start on the actual relatedness and how to actually leverage the relatedness to improve transfer learning and have multilingual machine translation systems. Yeah, thanks, Jay and Pranjal. And we'll take a break for 10 minutes.
Present the screen?
Yes, I will present it. It's
Maybe while we wait for the others to have a break,
yeah.
we try to extend the monitoring.
Yeah, go.
Yeah.
Feel free. Feel free.
You know, so in a multilingual machine translation, the focus was more on general multilingual. We didn't focus on class. Our main idea was to talk about general purpose translation. But you have now into scripts in Latin, grammatical similarities. I would say about 40% is overlapping, but then we have some more recent updates that we can show. That is the main focus. So and also this starting data creation and thought, right? That is completely new because that I was never covered over there. And in the for what I'll be talking about now for about R and 50 years, I would say 50% has already been covered. But you have food is good. Yeah. It's good.
Di bawah. Itu yang dipotong. Oh, besok. Enggak, sekarang bisa pakai. Oh, besok ada. Due to hardware limitations. topic. Share screen.
It takes a bit of time for that to,
Yeah.
no rush. Maybe it's not sharing this time. You clicked on something else.
Yeah.
It's doing the right thing. Okay, cool. Right. I just want to ask the online participants, can you see the slides? Can you see the screen?
Yes, you can see.
You can see it? Okay, awesome. So yeah, let's get started on the fun part, which is on modeling, vocabulary, and this is where we'll get into decision choices that affect massively multilingual machine translation. So there are three main considerations here. First is vocabulary, second is architecture, and third is training. So when it comes to vocabulary, I'm sure everybody has heard of subword segmentation, choosing the right vocabulary styles, choosing what languages, what balance. And one thing is, whenever we have multilingual models, we want to have a fair representation across languages. We don't want, like, suppose you're training on 10 languages, but most of your vocabulary, if it belongs to only English, then you're not going to get a good representation across languages. If you look at the, one second, if you look at the graph over here, then you can see that if you have, improper vocabulary balance, then you can have poor translation quality. By that, what I mean is, if you look at the red colored bars, those red colored bars, they represent no proper balance when you sample the vocabulary. And then the green colored bar, it represents when all the languages are balanced. And you can see that when you have a proper balance of vocabularies, then there is an improved translation quality because lower resource languages get a proper balance in terms of vocabulary. Okay, so how do we handle the vocabulary skew? Well, during the training phase of the vocabulary or the tokenizer, you have to make sure that vocabularies or the training data for vocabularies is sampled in accordance to adjusted probabilities. By that, if PI is the probability of sampling vocabulary from the language, then you scale that probability by the, this is a bit cropped out. Essentially what you do is you take PI to the power of 1 by T, where T is the temperature. So higher the temperature, the higher the chances of a lower probability vocabulary to be sampled. And then what happens is, if you have T equals to 1, which means you have the same sampling ratio as that of the original data, but if T equals to 100, then it means that all the vocabularies are sampled uniformly across the languages, regardless of the distribution. And over here, what you can see is what are the different performances depending on the temperature for vocabulary sampling. And it's kind of clear that if you take a vocabulary sampling temperature of around 5, then you get more or less the optimal translation qualities. But if you look very closely, the gaps in performance are not so much. So it means that vocabulary sampling or vocabulary ratio is important, but it's not extremely important. It will become more important when you're actually training. The training data ratios are more important than vocabulary ratios. So when does skew really hurt, right? So some people did an experiment and they found out that when you have character level representations for languages, or when you have very high unknown rates, that is when the translation quality starts hurting it really badly. So in the graph, it represents how much percent is English data. So when you have extremely low percentage of English data, of course, the English performance is going to be bad anyways. But if you have around, even if you have 99% of English data or around 90% of English data, the drop in performance is not so much. When you start having a high amount, like 99.99% of your vocabulary is in English, whereas 0.01% vocabulary is for other languages, that's when the error rate starts shooting up very hard. And that is one of the things we have to make sure. The lesson over here is training data balancing is a lot more important than vocab data balancing. So even if your vocabulary has a character level representation, it's okay. But you push it too much, you start seeing drops in performance. So when it comes to related languages, right, we know that, for example, if you take Indian languages, they're mostly related with each other. If you take a look at Indonesian languages, there are many common words. There is shared vocabulary. If you look at Romance languages, there is a lot of shared vocabulary. So in such cases, you have the opportunity to share scripts between different languages. That means you can also have compact models, and you can have smaller, because you have compact models and because you have smaller vocabularies, you can have faster training and decoding times. And this is very important in a production setting. So one of the things we can do is perform transliteration to boost cognates. So what are cognates? Cognates are basically shared common words between different languages. And there are certain approaches, like one of these things is called transliteration into English. So what we do is we transliterate all of our data into English, and all these transliteration mechanisms exist. So one such work is called universal romanization. There is transliteration of basically, if you consider Japanese and Chinese, these are two distinct languages. But it is always possible for you to convert Chinese characters, Chinese writing system, into the Japanese characters. So in Japanese, it's called kanji. In Chinese, it's called hanzi. And it's always possible to map from one writing system to another because they are historically derived from the same thing. So if you map from, say, kanji to hanzi or hanzi to kanji, it's possible for you to have better transfer learning between the two languages. And if you have small data for Japanese, but a lot of data for Chinese, then you can benefit Japanese translation quality from Chinese. And we have actually, this is one of the papers that I co-authored with a student, and we actually empirically proved that it can work during standard machine translation, but also when you have pre-training involved. Then the other thing is you can translate it into a common related language. So different from universal romanization, you can consider the case of Indian languages, where you have Devanagari script for Hindi, Marathi, Nepali, and so on. But languages like Tamil, they have their own script. Dravidian languages have their own script. But Indian languages are phonetically written, so you can always convert it to a common orthography. So if you map from, let's say, all the other languages to Devanagari, you suddenly have an opportunity to discover shared vocabulary from different languages. You can have a compact vocabulary, and we have shown in different works like Indic Bard, which I have done, and in Indic Trans 2, having this kind of shared vocabulary, it actually boosts the possibility of transferring from a higher resource language to a lower resource language. Now, there's a special case of languages called creoles. So what are creoles? Creoles, I mean, there's a long definition of creoles, but essentially you can think of them as pigeons that eventually evolved into languages. And these pigeons are fundamental, very basic languages involving phrases and words. But then when a person inherits these pigeons over some few generations, they end up becoming languages. And these are highly related to some very resource-rich languages, which are called as parent languages. So one such example is Mauritian Creole, which is very similar to French. And therefore, you have an opportunity to directly leverage French vocabulary without having to deal with any kind of vocabulary conversion. So we have some nice work on that, specifically focusing on Creoles. And we actually released a paper yesterday on machine translation and natural language understanding for 28 Creole languages, where we went all over the internet, got whatever data, and then we have machine translation models, we have data, and we have NLU models also. So it is a very interesting case of high quality transfer learning that can take place because of high resource-rich parents to resource-poor children languages. There is one also very interesting approach where you treat multiple segmentations of the same language as alternative sources. So for example, if you take the word potato, using a subword segmentation mechanism, you have the possibility for it to be segmented in multiple patterns, especially if you use methods like DP drop, where you have some stochasticity in the segmentation. So this paper by Khambatla et al., they showed that multiple segmentations of the same sentence can be leveraged as multiple sources. So it means that multiple segmentations can be treated as related languages, and that can actually help you boost translation quality. So the intuition is not very clear, because how can you see the different segmentations as different languages? But it turns out that they showed that you can leverage some amount of redundancy in various representations. And a differently segmented sentence can be considered as, okay, if you have, let's say, a language like Indonesian, we have Indonesian and we have Malay. Both are highly related languages. So they're almost identical, but not exactly. And therefore, you can treat them as slightly different segmented languages. And that is a way of considering relatedness via segmentations. So I'll get a bit more detail into what this universal romanization is. We have this sentence written in Chinese script, and there are two ways of performing romanization. One is dropping the accent information when you do romanization, and then the other one is to retain the accent information. And people have shown that retaining accent information is a lot more important when doing romanization, training multilingual models. So just keep in mind that if you're ever doing any kind of romanization activities, try to retain the accents. By retaining accents, you do lose the possibility of overlapping between different vocabularies. But accents are important. They tell you something more about how a particular word is. Because in Chinese, there are many similar sounding words if you drop the accents. And that means you cannot just drop these accents or these intonations. You have to be very careful. And as I said before, when it comes to family-specific transliteration, so you have the input text, which is Rajasthan. It can actually be written in another language. I think this is one of the Dravidian languages, and it actually reads as Rajasthan, but you wouldn't know it because it's in a different script. So it's possible to always map it into a common script like Devanagari, and this will be able to boost relatedness between different languages. As I mentioned before, Indic BART, Indic Trans 2, and then a more recent work called Relate LM, they have all focused on mapping to the highest resource language. And when it comes to Indic languages translation, we have found out that this mapping really boosts translation quality. But we can probably go a step further, is instead of having even the Dravidian languages, which are a bit distinct from the Indo-Aryan languages, if you just map everything to Devanagari, maybe it's not always a good idea. So you can consider two different groups of mappings, like Dravidian languages all map to a common Dravidian language, and Indo-Aryan languages all map to a common Indo-Aryan language. And that might be a better solution. So just to give you a very good reason to do this script mapping, if you look at this table, what we did is we compared what happens in zero-shot translation quality as well as supervised translation quality using script map language and non-script map language. So the first line, it represents a script map pre-training model, and the second line represents using individual or original scripts for each of the languages. And you can see that sharing the scripts led to better translation quality by up to 2 points in many cases. So this is direct empirical evidence that using a common script when training models for similar languages actually enhances transfer between languages. There are also some other works like increasing alignment loss by taking dictionaries. And if you know that you have dictionaries between different languages, you can actually impose certain losses on top of the additional standard pre-training losses or NP objectives, and you can enhance the translation quality even further. So now, what happens with zero-shot translation? Now, you will have noticed that models like NLLB, models like Indic Trans 2, they were never actually trained for anything beyond a certain specified number of languages. So, for example, Indic Trans 2 was only trained on 22 languages. But we've noticed that even though it was trained on only 22 languages, when experimenting with certain unseen languages like Bhojpuri, Awadhi, and so on, actually they exhibit certain translation quality. So even though the models have not explicitly seen these languages, they are able to perform translation. And one of the main reasons for that is that everything was mapped into a common script during training of these models. One other important approach over here is to induce artificial noise during vocabulary training. So for example, right, you have this high resource language, which is Hindi, where you have this sentence which talks about some initial cases of disease. So some researchers, what they've proposed is you induce some kind of noise at a character level or at character spans. So for example, the word is replaced by these red characters, which is going to be just some noise which has been induced at the character level. Maybe replace one character by another character and so on. But if you look at languages like Bhojpuri, these actually have this particular vocabulary item at the beginning. So by inducing some amount of character noise, you can have some potential for modeling a very highly related low resource language. And what happens is, if you train a model on this character corrupted sentence, then you'll actually be able to translate from a language for which we don't have any parallel corpus at all. So it is possible to induce some variations in sentence structure, variations in vocabulary, and end up with a very high translation quality for unseen languages. Now, one orthogonal approach is to think about word order. So you have the SVO, SOV word orders, right? English has the verb in the middle, but in case of Indian languages, there is a free word order. Typically, the verb is at the end. So some researchers, what they have discovered is when you reorder the sentence of one language to follow the word order of another language, it enhances the transfer between these languages, and you can actually get an improved translation quality. And this has also been explored in other papers, which focus on syntactic differences. There is a paper most recently on prompting, which showed that having monotone word order helps improve translation into related languages. So if you're translating from Hindi to Marathi, Hindi and Marathi have slight word ordering differences. But if you edit those sentences to have identical word order, then it actually helps improve translation of test sentences. So this is one important thing, that when you're considering highly related languages, think about monotone word orders. That might also help you simplify the attention mechanism inside these models. So overall, you have to make friends, not enemies. So that means you have to share vocabulary if possible, ensure balance between different languages, consider noising mechanisms to enhance transfer. You also should consider leveraging dictionaries and perform reordering of words or consider different word orders if necessary. So the next thing, which is very important, is the architecture. And everybody knows, right? There are three main types of architectures, which is encoder models, decoder models, and encoder-decoder models. And for natural language generation, typically what we do is we use either encoder-decoder models, or more recently, as it's getting popular, which is decoder-only models. But over the entire discussion, it will become clear that encoder-decoder models are probably the ideal models for machine translation. No matter how hard you try, you cannot simply beat encoder-decoder models for machine translation. But I'll get to that in a bit. So we do know that there are these basic architectures, but we're talking about massively multilingual machine translation, right? So how do you become massively multilingual? One is increase the number of languages. But if you start pumping in too many languages into a single model, it's going to hit a limit in terms of representation. You can't just keep stacking layers on top of one another, because the model becomes too deep and that the training becomes more complex. So what is an alternative is to have sparse models, which can typically be modeled using mixtures of experts. So there is also an intermediate between dense models, which is your standard transformer models where you do only stacking, which is called hybrid, where you have some kind of experts only after the last layer. But that's not very popular. The most popular one these days, I would say, is mixture of experts. So what is a mixture of experts? You know that in transformer models, you have feed-forward layers. But instead of feed-forward layers, you have n feed-forward layers, all in parallel. But you have to decide which feed-forward layer the current sentence's representation is going to go to. So what happens is that there is a gating mechanism which decides the probability of routing to a particular feed-forward layer. And this is called as a mixtures of experts. So now mixtures of experts can have different variations, but the most common variation is that the gating network tells you up to k experts to route the information to, and then you take a sum of all of these k different experts. If you set k equals to 1, then only one expert is chosen. If you manually set the experts, then you have the option to route information to a particular expert that you think would be ideal for a particular language. So you can think about it. If you want to have language family specific experts, you can have an expert for Indo-Aryan languages, you can have an expert for Dravidian languages, and so on and so forth. So there are many different possibilities of innovations for related languages over here. The one key problem is these MOE models are hard to train, and there have been some advancements like STMOE and so on, but it's more about being aware of what works and what doesn't work. It involves a bit of hyperparameter tuning. So it is true that you can boost your model parameters to several billions while not going too deep, but these are hard to train. So be a bit careful. Now, one interesting thing in the NLLB paper is they analyze for every language what is the expert that is preferred. So they did some analysis on the gating vectors and the gating routing probabilities, and they actually found out, I don't know if you can't see very clearly over here, but what it shows is similar languages typically get routed to the same expert. So automatically, related languages are already preferring certain specific experts. That means if we blindly just decide, okay, this expert will be designated for, let's say, the Indian languages, it's not going to be such a bad thing. And there have been some more investigations that language families have similar gating behavior. So there is a reason to believe that related languages will prefer certain experts. I want to make a small note on LLM-only machine translation modeling, where, in LLMs, we have causal attention mechanism, right? So if you want to do machine translation using LLMs, you take the source sentence and then you ask it to generate the target sentence. There is no separate encoder or decoder. There is only one single decoder. But the problem is, this is called as the causal LM-based machine translation mechanism. But in an encoder-decoder mechanism, remember that the encoder allows the source sentence to attend to all tokens. And if you just limit it to look at future tokens, that might not lead to optimal source representation. So some people have come up with what is called as the prefix LM, where you have a bidirectional mask for the source sentence part and a unidirectional mask for the target sentence part. So you can see that causal LM has a kind of a lower triangular matrix, but this is a kind of a hybrid matrix, which is a rectangular matrix or attend to in both directions for the source part, but for the target part, you only have causality. And people have shown that this leads to better translation quality for machine translation using decoder only LMs. It's a simulation of an encoder-decoder model inside a decoder-only model. And keep in mind that you can take a pre-trained llama model, you can take a pre-trained blue model, and fine-tune with this kind of a prefix LM style, and you should be able to get better translation quality. Now, you might be disappointed by looking at this. If you look at the blue line, that's the encoder-decoder model, and the x-axis represents the number of parameters. No matter what parameter scale you have, encoder-decoder models tend to beat all the causal LMs and all the prefix LMs. Prefix LMs tend to be a bit more closer to encoder-decoder performance, but given that encoder-decoder models are more straightforward to train as compared to these prefix LMs, you can see that standard causal LMs will never be able to beat encoder-decoder models. However, what is interesting is the zero-shot performance of these decoder-only LMs. And you can see that encoder-decoder models actually fall behind the prefix LM models. So that means that these large language models, if tuned properly, you can get the best zero-shot performance. And that is one of the hot topics recently. So you might want to also further go deeper and see what is the zero-shot transfer for related languages. You might zoom into the case of related languages and maybe observe that when training on related languages, you can get a higher zero-shot performance than training on unrelated languages. So that would be one round of investigation. I'm not sure if anybody's done it, but it is something to consider. So what is the summary of this thing? You have to make wise choices when you're modeling. And the first thing is you want to scale up, you have to use mixture of experts. These are challenging, but the rewards are very high because at the end of it, and I'll get to this when I talk about compression, during training, and you might have explosive number of parameters, but during decoding time, you can significantly cut down on the number of parameters while retaining performance. And I'll get to that. It is good to design language group specific modules, like for example, have an expert for each specific language family that can give you very good performance. You have to be careful about positional encodings and normalization. Actually, that's a slide I skipped, but please take a look at it. It has implications for zero-shot transfer quality. Dense models are, of course, not ideal, and LMs are decent empty models for zero-shot situations. And always, if you're using LMs, prefer the prefix LM style rather than the standard causal decoder mechanism. Now, third thing is training. So what you could do is you can take all the corpora, bunch it together, pump it into the pipeline, and get a single model. But this is very dumb, right? That means because you don't have any control over the different balances of corpora, you don't have any control over gradually incorporating information. And people have shown there has been interest in curriculum learning. It means the order in which you give your data will always be important. And if it comes to the concept of related languages, you have to consider stages. So what does that mean? So you have a subset of corpus, you have an initial stage of training, and you get an initial model. Then you make some modification to the model, maybe you add vocabulary, whatever, and you have additional subset of data, which might include some of the original subset also, train a second stage model, and so on and so forth, where you have multiple cascading stages one after another, which continually add to this existing model, or sometimes you will subtract from the model. For example, think about it. We have biases. We have some toxic words that the empty model might generate. So you might have one stage of general purpose training where you don't care about toxicity, but then in a second stage, you might want to delete this toxicity by fine-tuning on certain. In one stage, you might have general language independent performance, but then you want to narrow down into a language family specific performance. So then it is possible to use multi-stage learning in order to induce certain behavior. So when you do joint training, right, you have a batch which consists of multiple language pairs. And all you need to do that is mix all the corpora, shuffle, and then choose batches. It is very useful for fully shared models, but models sometimes can have separate language encoders or decoder, in which case you're going to have to route information to the encoder and decoder. But nobody wants to do that. Nobody wants to have multiple encoders and decoders. We want all of these routings to take place automatically. That's why mixture of experts is a very nice thing, because there's a gating mechanism that takes care of all of these things. Now, are language family specific models better? Again, we're going to get to this particular question. We answered it from the perspective of vocabulary, but what about actual language relatedness? And what one of the experiments that we did, this is actually from my PhD thesis, where I had trained different types of models. So there is a parent language and there's a child language. So for example, I took Turkish and Hausa and trained a joint machine translation model for Turkish to English as well as Hausa to English. And similarly, I had Hindi and Marathi. I trained a joint model. And if you look at it, Hindi turned out to be the best combination language for the three Indic languages that I had experimented. If I look at Arabic, it was better for Hausa because Arabic is closer to Hausa than any of the other languages. If I look at Turkish, Turkish is not that very related to any of these languages, and therefore it didn't actually give the best performance. But Arabic is also very close, a lot closer to Somali than any of the other languages, and therefore Arabic actually gave better performance. You can't see the score, but you can see it in the side state. So what does that mean? You should try to use similar languages during multilingual training. Now, this is just the case for two languages. But what happens when more languages are trained? So in this last column, you can see that I trained multilingual models for a language family and multilingual models with some random selection of languages. And I took the difference between the performance. And the fact that language family specific models had better scores indicated by the positive improvement means that it is always better to train a language family specific model over a language agnostic model. This is again a very important lesson that relatedness enhances the possibility of transfer learning, and therefore you should always choose to have family specific models rather than family agnostic models. And during the vocabulary section, we already covered how to boost this said relatedness by vocabulary mapping, script mapping, romanization, and so on. So now you might just tell me, right? Why did you even come up with this hypothesis? What is your proof that relatedness is there? You must have done some random experiments. Well, actually, in Kuduganda et al., they actually did an analysis of a multilingual representation space where they took language embeddings and they mapped them into a common shared space. And you can see that actually the embeddings for different languages, they end up forming different clusters. So this cluster over here is the Indo-Aryan cluster on the top right side. On the bottom right side, there is the Niger-Congo cluster. So it means it's not just that me telling you that there are related languages. The model actually sees related languages being mapped into a common subspace. So if the model sees it, why don't we make the model's task of inferring these things by just training language family specific models? This will actually reduce the burden of learning things. It will make smaller models, more compact models, and there'll be better transfer learning between these languages. Now, one thing is, linguistically, we know that Indo-Aryan languages are similar, but can we also determine these empirically? And yes, in the previous slide, as I had shown, that models actually see certain languages as similar. Some people have done the study by taking these language embeddings and perform clustering on these language embeddings. And even based on these language embeddings, right, it is possible to see these clusters. So again, you can't see this bottom part of the, let's say the tree, but it actually shows, I think it's fine. I can get to the essence. The essence of it is that if you do clustering based on language embeddings, you actually can identify, let's say, clusters of languages in similar languages. And in the next slide over here, which is more important, you can see that if you look at randomly clustered languages, the performance is something. But if you take family-specific languages, determined actual linguistically determined families, you get some performance. But if you do empirically determined language families according to embeddings, then you end up getting more or less the highest possible performance. It's not that far ahead of family-specific linguistically determined families, but it is there. So either you use lessons from the model itself, or you just decide your own language families and train. And that is good enough. So this is not just some game that anybody came up with saying that, oh, just train on related languages. There is hard evidence, empirical evidence, which shows that relatedness is a very important. Now, there are other things like you can have adapters. So you may have heard of these adapters, right? Low rank adapters, efficient fine-tuning mechanisms. In fact, I would say that there are some people which have shown that there are family-specific adapters. So when you're fine-tuning to induce, let's say, 10 more languages, it is better to have family-specific adapters where you have one adapter for one family, another adapter for another family, and that could also enhance transfer learning between new induced languages. Now, one other important aspect is multitasking. So we've already shown that multilingual training is good, but multilingual and multitask training is also good, and that really works for related languages. So Ali, in their paper, what they showed is you have to consider inducing noise during training, but also have paraphrasing as a source of noise. So paraphrasing you can think of as a related language. Think about it. If I have a sentence in one language, if I paraphrase it, it is not the exact same sentence, but you can think of it as an alternative sentence or a related sentence. So this is a kind of relatedness. And they've shown that when you do this kind of multitask training with paraphrases and noise, you end up getting a better transfer learning between different languages, and you end up getting higher translation quality. So I encourage you to take some time to actually look into this paper. It posits that multitasking is a very nice way of further enhancing transfer, not just between languages, but also between tasks. And a more recent paper in 2021, where they talked about having multitasking, but to enable translation into a language for which there is no parallel corpus. So what they did is they have English-Hindi parallel corpus, they have Hindi monolingual data, and they have Marathi monolingual data, for example. And they gave recipes of multitask training, which involves translation, denoising autoencoding, back translation, and adversarial training to get a translation direction for English to Hindi or Hindi to English, but then push the Marathi representations close to Hindi. And that typically is taken care of denoising approaches as well as adversarial approaches. Think about it this way. I gave a Hindi sentence to the encoder, I give a Marathi sentence to the encoder, and I ask the encoder to classify between the two languages. It will do the job very easily. Now, if I backpropagate correctly, it will just separate the representations of Marathi and Hindi. But what if I backpropagate with a negative gradient? It will confuse Marathi and Hindi representations even further. So if Marathi sentences can align themselves because of script similarity with Hindi, then this will push Hindi and Marathi representations to be more and more similar. And therefore, just by using Hindi-English parallel corpus and Marathi representations that are more closer to Hindi, you can get improved Marathi-Hindi translation quality. So adversarial mechanisms are a very nice way of pushing representations closer. And during the vocabulary section, we had talked about inducing artificial noise in the vocabulary to make certain word forms in one language look similar to word forms in other languages. So noising and adversarial training are very nice ways of inducing higher relatedness between languages. And you can consider that as one of the possibilities. Problem is the pipeline is very complicated to train, but if you have the patience to train these, I think the code is publicly available for this work. So you can try this for languages for which you have no parallel corpus, but are related. Creoles might be a very nice application for this. Just to show you the results for what would happen is if you consider adversarial mechanisms, right? You can see that you can end up getting really high boosts in translation quality, especially for, let's say, Marathi to Hindi. You can get from blue score like 3.9 or 8.1 all the way up to 12.7. So adversarial mechanisms do really have a strong impact on the final translation quality. So think about it for related. Now, the other thing is, we've already talked about skew in vocabulary, but what about skew in training data? Hindi will have a lot more data, Marathi will have a lot less data. So we have to understand that we might want to oversample the size of Marathi data to have similar size to that of Hindi data. So you can oversample before training, or you can oversample during training. And how does that happen? Again, temperature comes to the rescue. So what would happen is, if you have PL, where PL is the probability of sampling a sentence from a corpus, then you can do PL to the power of 1 by I, where I is the temperature. And what will happen is, a high probability will become somehow low, but a low probability will become somehow high. And that will cause a balance in the different probabilities for different languages. And if you look at the figures on the right side, you can see that if you use the default data distribution, then the tail end or lower resource languages, as indicated by the green lines, you'll end up getting poor performance. But the high end languages, or the high resource languages, they will tend to have higher performance, of course. Because if you don't see the lower resource languages as much, of course you're going to get poor. But if you start balancing the corpora with, let's say, temperature of 5, indicated by the red line, you can see that the lower resource languages suddenly exhibit higher performance, because you're seeing the lower resource data much more frequently. And if you know that there is also a related higher resource language, then it allows that lower resource language to perform even better. So what would happen that if you use a very high temperature, it means all languages are sampled uniformly. It is good, but it really negatively impacts high resource performance. Because high resource, at the end of the day, you have to see it a bit more than low resource languages. Otherwise, you just overrepresent low resource languages for no reason at all, and we don't want that. So suffice to say, there is no clear recipe on what is the optimal temperature. But empirically speaking, 5 is a good temperature, because it kind of gives a good balance between equal representation and completely unequal representation. The performance skews are really, really visible for translation into English, because English is the most highest resource language. So the decoder really likes it if you balance the lower resource source languages while having as many English tokens in the target set as possible. So we've done joint training, where we've given everything to the model one at a time. Now we're going to talk about stage-wise training. And why stage-wise training? Because we've already seen that, right? There are many considerations when you have to train on 1,000+ languages. You can't just train all of them at the same time. So the good thing is, with stage-wise learning, you can incorporate new languages, and you can also expand the capacity of models one step at a time. So I'll come to what that means, right? Think about it. You have an initial model trained, let's say, on French English, but tomorrow you want to have a German English translation model. You can't just train a new model from scratch. That's too expensive. You want to use already what has been learned. So what if you can just add new German tokens to the vocabulary, expand the vocabulary, and continue training of the model on this German English data? This is good. It's possible. It will work. Why? Because you're already leveraging some kind of pre-trained knowledge for French English. But then, if you just fine-tune on German English, and especially if your data is very small, which is typically the case for extremely low resource languages, you might forget or lose a lot of information. So that is the case where if you have access to the previous stages data, like French English, a small amount of French English data, you can combine it with the German English data and then perform fine-tuning. In this case, you'll be doing a kind of smooth continual learning. And this approach is something that has been useful for domain adaptation, and people have shown that it also works for machine translation. So I have already explored this in one of my previous works, where I've shown that simply fine-tuning on a new language is not always good. You should always incorporate a little bit of the previous language. And it helps if this previous language is somehow related to your currently being the newly introduced language. So always consider relatedness when you induce a new language, and always try to use previous data from the related languages if it is available. Now, suppose you're introducing a new language, but you don't want to do it just by embedding, because think about it. English, French, and German are very related to each other. So you can reuse the capacity, the existing pre-trained information, you can use it effectively. But if you're just adding a new language, let's say Turkish, which doesn't have much to do with English, German, or French, then it kind of might be required for you to introduce some more encoder parameters, some more decoder parameters. So in such a case, what would happen is, you have that existing trained model, and you freeze all of it. You only introduce encoder for the new language, and you train only that encoder. So you keep most of the parameters frozen, but you train it only for that specific language. And the nice thing about this approach, by adding components stage-wise, by freezing everything else, is that you can have unintentional or maybe intentional zero-shot transfer from this new language to all the other languages that existed in the world. So if you had, let's say, English to French, English to German, and you wanted to introduce Hindi on the source side, then you can unintentionally, you can induce Hindi to German, Hindi to French translations just by training this Hindi component. So it should be possible for you to do this. And there have been some related works, and especially recently, this kind of, let's say, freezing and introducing new components has been useful for multimodal models. So people have actually created end-to-end speech translation models by first training a text model, then a speech transcription model, and a speech synthesis model, all of which map to a common representation space. So you freeze a central model, and then you cause all the other models to map their representations to the central model, and you can end up having a multimodal model in that particular way. Now, you've already trained models, but you still find that certain languages are showing poor performance, right? So suppose you train a model on English, French in the beginning, and then you added English to 10 other languages. But it will still end up showing suboptimal performance for some of the languages, because there are these things, some things you can never take care of. So here's where adapters come to the rescue. What are adapters? Adapters are just small feed-forward layers that you append to inject into the model. And what happens is that while the performance without adapters, like the base model might have poorer performance, adapters allow you to slightly boost the performance for certain languages, because you're now specializing these adapters for specific languages. So it means there is value to doing stage-wise training. During the initial stages, you can have a more generic model. Towards the later stages, focus on specific languages. But if the data for those specific languages is too tiny, rather than fine-tune the entire model, you fine-tune only adapters or specific components. This is cheaper computationally, and it allows you to get really boosted performance, as evident from this particular plot over there on the bottom right. You do end up adding a small number of parameters, and you do end up making the model a slight bit slower compared to the original model, because you do have more compute to do. But still, this is not a bad thing at all. So there has actually, surprisingly, despite adapters being relatively new, there has been a lot of work on adapters for related languages. So most recently, one of the works that I was involved in was doing distillation for related languages, where we had a model like, let's say, Indic-Trans, which focused only on Indian languages. And we did have some languages from Indo-Aryan group. We had some languages, let's say, from the Dravidian group. But then we also have certain highly similar languages, like Bengali and Assamese. They are highly related to each other. We have Odia, which is more related to Bengali as compared to, let's say, Marathi. So then we experimented with having adapters on top of a, like, let's say, compressed model, specifically adapters for these language family specific groups or subgroups. And we identified that having these language group specific or subgroup specific adapters are always better than using separate adapters, one for each language. So it is good for you if you can find adapters and share and train them on multiple languages or a subgroup of languages, especially if they're related to each other. It leads to more efficient solutions. So there are also these things called as hyperadapters, where instead of having separate adapter parameters for each new adapter that you're adding, you have a hyper set of parameters where you use embeddings to initialize adapters for that parameter. So you will have, let's say, instead of, let's say, if you have one adapter with 1 million parameters, if you have 100 languages, you have 100 million parameters. But instead, you can have a hyper network, which will only contain, let's say, about 5 million parameters. But this 5 million parameters allows you to initialize 1 million parameters for every single different language. And therefore, you can simulate 100 million parameters, but with significantly fewer parameters. So this is called as hyper adapters. And this is kind of related to this concept of contextual parameters. And essentially, it looks like this. You have a parameter generator model. So you no longer have independent parameters, but you have a parameter generator model, which then gives you the parameters for the encoder and decoder mechanism, which is then trained. So you backpropagate through the generated parameters, which affect the parameter generator. So there is a meta network which generates parameters for you. And this allows you to be very efficient. And even in this work, they actually showed that parameters which are generated for similar languages are somehow similar to each other. So there is a concept of relatedness even in meta-parameterization. Again, this is a bit of a dense topic. I would again recommend going to this paper. It might give you some ideas on how to analyze these meta-parameter models. Yeah, as I said, right? If when you do this kind of, let's say, meta-parameterization, you actually identify that these meta-parameters also encode certain concepts of relatedness, where the embeddings for, let's say, related languages like Gujarati, Bengali, Hindi, and Marathi on the top side, they have similar generated parameters when you use this kind of hyperparameter approach. Further, from one more paper is using a adapter for a specific language pair, using an adapter for a language family, and using an adapter for language agnostic groups. And they found out that using language family specific adapters gives better boost in performance as compared to language agnostic parameters. So once again, relatedness comes to the rescue. All of this is empirical, all of this is backed up with numbers. Now, one small thing is what happens for languages like Creoles. Creoles are very related. Like, for example, Mauritian Creole is highly related to French. So you don't need to induce new vocabulary over here, but you need to identify which language is the best parent language for a given Creole. So for example, if a Creole is originated from Spanish, then it is better to use the vocabulary of Spanish for that particular Creole's fine-tuning stage. If you use the vocabulary, let's say from German or let's say from Hindi, we might not get ideal transfer learning performance. So you have to be careful about the related parent language when you deal with languages like Creoles. Now, we have already established that there is a certain amount of curriculum that is involved. So you can, one of the things that we did for Indian, like Indic Trans 2 is we had 4 stages. The first stage is we trained the model on all of the data, parallel training data we had available. And then we fine-tuned it on very high quality clean data. We use this model to generate back translated data or forward translated data. We generated a huge amount, like 400 million byte express just by byte translation for 22 languages. We trained the second stage of model on the original parallel corpus and the back translated or forward translated corpus. And we fine-tune this again on clean corpus. Why am I getting to this clean corpus part? Because we observed that when you have this clean corpus stage training, so if you look at, let's say, the red colored bars and the green colored bars, you can see that the red colored bars, which involve fine-tuning on clean data or seed data, they always end up giving you boosts in performance as compared to their counterparts, which do not have any kind of fine-tuning. So remember one thing, always be aware of using clean data for fine-tuning. Your final stages should always involve some kind of clean data because it always gives you boosts. So what is clean data? Clean data is basically human curated data. You know that it is of high quality. And if your model finally has seen clean data, it will tend to generate more cleaner representation. So just it's one small tip that we have. Now, this is one slide on the importance of curricula. There is some recent work on using different types of curriculum. I'm not going to go through this in the interest of time, but please consider looking at it. Instead, what I'll do is I'll summarize. One thing is always build your models incrementally in stages with curricula if possible. You add vocabularies applicable, add it for distant languages being introduced, but no need to do that for similar languages. But small amounts if you want to have, let's say, slightly related languages. You should try to freeze for efficiency and not for forgetting, which means use adapters. If you have, like, say, only 100 examples of fine-tuning, which is already pretty low, don't fine-tune the entire model. Try to use adapters. Try to use small newly induced parameters. Try to leverage noise, paraphrases, adversaries very wisely. So try to use multitasking during training. Use group-specific models and adapters, and always be careful about the balance of languages. Use temperature very wisely. This is an important recipe for training these high-quality, massively multilingual models. Now, we've trained a very big model here, but we can't just deploy it. We can't put up a 175 billion parameter model on a single GPU. It's going to incur a cost, and I'm pretty sure that it's not good for business. So, you want to make them smaller. Why? Because we already know that with a lot of parameters, you can have high translation quality but slow speed. And if you have fewer parameters, you can't have that good translation quality, but at least the speed is fast. What we want is less parameters, high performance, high speed. People have kind of already shown that distillation is a nice way of doing this thing, but there are certain nuances. One simple approach is to do pruning. So you train an initial model, you identify which parameters or which neurons are not so promising, and you'll notice one thing. When you train a model, 80% of the parameters are close to zero. So that means you can actually delete 80% of the parameters, but you still need to train with a large number of parameters. These 80% of parameters become zero only later during the training. You still need them for the initial part of the training. So you can decide what part to prune out. But if you prune out, of course, the model's behavior will change. So you need to readjust the model's performance. Therefore, you need to train them again. So this is an iterative process where you can first prune, then fine tune, then prune, then fine tune again. And while I'm not very clear on the specifics of pruning, there are two main approaches. One is structured pruning, where you remove specific layers. And then there is unstructured pruning, where you remove weights according to some kind of choice that you have to make. So for example, you have 1 billion parameters, you sort them according to their magnitude, and you get rid of the lowest k, let's say. But when you do structured, you decide delete the k layer, delete the k-1 layer, and that is another mechanism. People have shown that unstructured pruning, when done properly, is a very complicated thing, but is more effective than structured pruning. Because structured pruning involves logic, and we've known that in deep learning, logic doesn't always fly well. Sometimes you have to do some kind of, let's say, unusual things, and unstructured pruning tends to work a bit better. But then there is some more insights behind that, which I am not intelligent enough to understand because I didn't go through the papers. But I can say that you might want to take a look at unstructured pruning to see how exactly it works and why it's better than structured pruning. Now, you know that there is the NLLB 200 model, right? So 54 billion mixtures of experts model. But again, this model needs 4 GPUs of 40 gigabytes in order to perform decoding. And again, you can't do that. You can use something called as quantization, which I'll get to, but it's just infeasible. Some people have figured out that you can use expert importance in routing probabilities. So for example, if for a specific language, you know that the first 2 experts are better than using the remaining 20 experts, you just delete the remaining 20 experts because you're not going to use them. That drops the performance a little bit, but it allows you to have a very, very lightweight one. And as we already know that related languages typically cluster to the same, let's say, same expert, you always can reliably get rid of k experts and expect that the remaining experts, which work good for one language, will also work well for other related languages. So it's a nice quick hack. There are different things, but I would say that look at this particular paper on memory efficient NLLB. It will give you ideas on how to first build and then prune models. And it's a very interesting piece of work that I've done. The second is quantization. So what does that mean? You decide certain parameters that will be quantized or converted into a lower precision format, and a small fraction of weights which will be very difficult to quantize, and therefore you leave it in higher precision. And this was in the LLN.intake paper, where it shows that, let's say, 99% of the parameters can be converted from 32 or 16-bit to 8-bit, and 0.1% parameter, like, or 1% of parameters stay in higher precision. And if you do this, you can literally cut down your requirement by half, 1/4, as having, depending on the higher precision that you use. In fact, we go a step further, and there are 4-bit precisions now. There is QLoRa, you may have heard. And QLoRa actually allows you to go to a more lower precision. And they've shown that going up to 2 bits sometimes is still okay. So it means that once you've trained large models, you don't need to decode them with those many high precision parameters. You can always go to lower precision. But how this impacts related languages is still something in question. Does going down to low precision for one language necessarily have the same implications for another related language? That is a question that needs to be investigated. If it is the case that going down to low precision for Hindi doesn't deteriorate Marathi's performance, then that is a global decision that we can make. Otherwise, we have to take a large model and have different levels of precision for different languages. And that is going to be an extra consideration. So some investigation might be taken. And yeah, this is just a plot which shows that the lower precision you have, the poorer the performance, but it doesn't degrade by that much. So the final thing is using distillation. Now distillation comes in 3 flavors: word level distillation, sequence distillation, and interpolation, which is just an interpolation of word and sequence level distillation. So word level distillation is called online because you use the distributions of the parent model to perform the cross entropy calculation for the child model. See, offline distillation involves you taking a pre-trained model, translating all of the data, and then using this generated data as labels for training your compact models. So offline distillation is a way of learning your model's data distribution. But online is a way of learning your model's actual probability of generation distribution. If you have 54 billion parameter models, you are not going to be able to happily translate all of those sentences in an offline mode. So therefore, it is better to use online distillation. And in NLLB, actually, this is what they've done. They've trained a large model, they perform some kind of domain adaptation, and then they do a word level distillation to have smaller, denser models. By the way, smaller models can be dense. We don't really care about MOEs at that stage because MOEs at smaller scales don't really make sense. So, but I don't know, maybe there is some open space for small MOE models. Maybe it might be interesting, but to my knowledge, the cost benefit of denser models is better at smaller scales. And these are some results which show there is a 54 billion parameter model with a certain behavior. Note that you will always end up losing performance no matter what you do. But if you have a dense baseline without distillation, you have, let's say, blue score like 43.5. With distillation, online distillation, you can actually increase the performance. So do consider online distillation. And again, how the implications are for related languages, it's still an open question. There is some work that we have done about distilling for related languages. You might want to check it out. I've put the link in this particular slide. So the holy trinity is you prune and tune, you consider online distillation, and you perform quantization as required. Quantization should typically be your last step. You always wait till the end to quantize. There is also something called as quantization aware training, where you perform quantization and learn the specifics of quantization during training itself. I don't know too much about it, but I do know that it exists. So you could take a look at it also. Now, I'll quickly go over the last part over here, which is very important, which is implementations and toolkits. So everybody knows the big four, right? There is FairSec V1, V2, which is very comprehensive for machine translation, pre-training, and fine-tuning. There is transformers. It's very good for fine-tuning, but maybe if you want to train from scratch, it's not an ideal toolkit. It's very popular. Everybody knows. There is Tensor to Tensor, which is deprecated now. But back when I had started working on transformers, this was my go-to. It was very easy to train models, but once PyTorch started becoming better and better, people have gradually shifted to PyTorch. But if you look at this toolkit called Trax, which is based on JAX, it's very efficient and you can use it for training at scale, but it is still not as popular as PyTorch, I would say, for machine translation. And then everybody knows OpenNMT. This is one of the oldest toolkits as far as we know. And it has both PyTorch and TensorFlow, but it is obviously not as popular as FairSec. Now, the main problem with these four toolkits is they have very large code bases. They're released by big groups, and they have every single folder with tens of models, hundreds of models, small variations, adding new code. Like think of a new student who comes in. You say like, hey, why don't you implement this? Take a look at the folder, 100 files. They're going to be overwhelmed. They'll be like, sorry, I'm not going to do this. Most of them just get depressed. So therefore, there are more beginner-friendly toolkits. One beginner-friendly toolkit, if you don't care about the implementation, but you care about speed, is MarianMT. It is written in C++ and it has minimal dependencies. So if you want fast, if you want more deployability, you want faster training, definitely use MarianMT. JoeyNMT is for real beginners, for students. So if you want students to get started on machine translation, JoeyNMT is very nice. There is Sockeye by Amazon, which is again a bit more complex than the other toolkits, but it is apparently very good for distributed training and efficient inference. And then finally, YNMDT by me. I created this over the past 2-3 years. And I did design this toolkit to actually incorporate anything I found interesting. So I read a paper, I find something interesting, I implement it. It's a fun side project that I have. And I do have a lot of focus on multilingualism, pre-training at scale. So if you actually want to pre-train, let's say, a BART model of 2 billion parameters, it's possible. I have implemented FSDP and many other things. Yeah, it is a bit of shameless self-promotion, but I mean, you can consider taking a look at it. And if you have any suggestions to improve it, I'm always happy to incorporate it. And that, I think, is the end of whatever I'm saying. We will take questions at the end, but I'd like to hand over to Jay and Pranjal to quickly go over the final bits of our talk. How are we on time? We have 15 minutes?
Yeah.
Oh, awesome. I did well then. Pranjal, Jay, if you can take over.
Sure. I think I don't have the permission to share the screen. So
Oh, let me stop sharing. Now you can.
um, is the slide visible? I believe.
Yeah, it's visible. Let me just side by side standard.
So many time, 45 more minutes.
We have 45 minutes?
Yeah, till the end.
Really? Okay, that's nice.
Till the end.
We can have a lot of Q&A then. Okay, yeah, go on. We have a lot of time,
Okay.
Jess. Just take your time.
Sure. Yeah. So now so far we have looked like how to collect data as well as train model and what are different training strategies for these models, right? And also which architectures to employ. So one of the things now, like let's say in order to actually like see right how good the models like that we have trained are, right, is evaluation. And this is something that should be like done more robust, basically carefully and to ensure that the models are, let's say, robust and also like consistent in terms of comparison, right, across different systems. So now in terms of different MT metrics, right? Sorry, is there anything?
That's okay. No
Okay.
problem.
Yeah. So now in terms of the like broad taxonomy, right, for MT evaluation, or at least what metrics are there. So there are broadly two types of metrics which are used for evaluation. One are basically like string-based metrics, which are untrained. So they are just used out of the box. And the other ones are trained metrics, where usually you have, let's say, a model which is trained for ranking or basically scoring the translations. And now basically within each of this, right, let's take a look at what each metrics are and yeah, the differences between them. So now if we look at basically string-based metrics, so string-based metrics are mostly capturing lexical similarity. So let's say given us candidate translation as well as reference, how closely my translation is with respect to reference, right? So it's eventually optimizing for precision in a way. And in this case, there are two approaches. One is word level, where you do word level n-gram matches, and the next is character-based n-gram matches. And the metrics which are popular based on word level are Blue, Meteor, NISC, GTM as well. And the other one for character level are CHRF and CHRF++. And there is also one more line of metrics, which is calculating edit distance and basically understanding if the translations are good or not. And that's translation error rate and word error rate. Now coming to the model-based metrics. So in model-based metrics, there are two ways. So first is like we have trained, like let's say pre-trained language models, right, which have been trained on extensive amount of web corpora. Can we use them directly out of the box and basically generate contextualized representations, right? And using that representations and scoring it in some embedding space, right? So there are two approaches for this. One is like standard word embedding based approach, where you just learn the embeddings. And next is contextualized embeddings, where you just use an existing model such as BERT or BART and just compute the scores based on the representations. And apart from that, another line of work is more of supervised models, so which are expertly, where you expertly fine tune, let's say, pre-trained models, right, encoder models on a regression task where the model has to generate a score. So basically how good or bad the translation is. And otherwise, like given like multiple translations, model has to rank the best translation out of all those choices. So in this case, like the popular metrics are BLERT and COMET. And there's also BERT for MT as well. Now, okay, so one thing is like, let's say we now have more model-based metrics, right? And one of the advantage of model-based metrics is that they tend to correlate better with human judgments, right, compared to string-based metrics. So can we really trust string-based metrics nowadays, right? Like given that we have much better metrics than that. So in order to answer this question, Sai et al. Conducted a study where they compare the correlation of different string-based metrics with human judgments for Indic languages. And they find that out of all the string-based metrics, CHRF and CHRF++ are the most reliable. One more point is whenever we are basically doing string-based evaluation, right? Like using any string-based metrics such as Blue or any other metrics, you should definitely do significance testing in order to validate whether your translation or at least from your system is significantly better than the other baselines. And this was at least like the result for Indic languages, but does it mean that blue can't be trusted, or like we should not use blue. So to broadly speak, blue can be a good diagnostic metric, which can provide you a macro level analysis, basically filtering out really, really bad systems. But if you want a more fine grain evaluation, right, like CHRF and CHRF plus plus tends to be a better choice in terms of string-based options. Now let's take a look at model-based metrics such as Comet and how they are trained, as well as what sort of training data we need to basically train such models. Right? So in this case, we have source, translation, as well as a reference. And note that the reference can be optional. And now, given this inputs, right, like this source, translation, and reference, the annotators need to score whether the translation is correct as per the source or not. So here there are two ways. One is a direct assessment, where you just ask the annotator to basically rate the translations between, let's say, a range 0 to 5. The next one is a MQM metric, which is multi-dimensional quality metrics, where the idea is you ask the annotators to actually highlight different spans of candidate translation where there are errors, and also basically rate the severity of errors. So for example, if you take a look in the image, we can see there is a source sentence and corresponding Google API translation available, as well as reference. And here for the Google API translation that is available, different segments are highlighted with different errors and also marked with severity. So now, okay, once let's say we have like this different spans and its errors, how do we actually like calculate the final score, right? So one way could be to actually use these annotations and do a weighted sum, right, based on some heuristics or formula. And that's how we, let's say, get a MQM model, right? MQM annotation basically. And now we have this two different flavors of data, right? One is a direct assessment, and next is a more MQM data, which is a bit more fine grained. We can now just use any pre-trained, let's say, multilingual model of our choice and fine tune it based on regression, right? And there are two models that we can get, right? Comet DA and Comet MQM. So for Comet, they use XLM Robota as the base model, pre-trained base model to start with. Next, let's say, okay, that Comet, let's say, have been trained or at least calibrated, right, on a certain set of languages for direct assessment. But still, the main issue with, like, let's say, a model-based metrics is, right, that these metrics are work well on the languages which are, let's say, correlated or at least related languages, right? So maybe there is not like a optimal zero-shot transfer, right, for the languages of your interest, which you want to evaluate the models, right? So in that case, what you can do is, right, if you want to just adapt the existing pre-trained Comet models, right, this would be the recipe that you need to follow. So let's say you will have, this is an example for Indic, but the same will apply for your language use case as well. So you take Indic direct assessment data and the existing Comet DA pre-trained model, and you fine tune the model on this data and you get Indic Comet DA, and same applies for MQM data as well. So this is how you would like see, let's say, if you want to adapt or recalibrate the models, right, to work well for your languages, this is how one should go about it. And the following table, you can see that the Indic Comet MQM tends to have higher correlation with human judgments for a certain set of languages. And having this higher correlation also influences other related languages which you want to evaluate and enables like good zero-shot capabilities. So now, okay, like we know that, okay, that let's say this model-based metrics have better correlation with humans, right? But if you want to even like consider this model-based metrics as well, right? You should consider it with some caution, because like this is also not a perfect or like a go-to solution, right? So one of the let's say issues with this model-based metrics is, right, that they are directly based on the pre-trained model, right? And this pre-trained models might have certain biases, right? Which might not be directly easy to fix during fine-tuning. So for example, Amenhen et al. Finds that Comet makes mistakes and is not sensitive to numbers or named entities. And this insensitivity could also affect the scores of the final translation as well. Similarly, Moge et al. Shows that there is poor quality estimation with downstream performance. So for example, whatever the metrics that we saw right now, right? They tend to have negligible correlation with the extrinsic evaluation of the downstream outcomes. So basically, like how the translation should be and what sort of like quality expectations that humans have, right? They tend to have like negligible correlation with it. And one more thing is the metrics that neural-based metrics that we saw, right? These are not very interpretable. So which means that, for example, in Comet, the scale ranges are nearly the same. So it's very hard to identify between two different systems which one is significantly better than the other, if based on just the numbers at least, because the scores are nearly same. Apart from that, like another suggestion that the paper says is you should have, like if you have diverse references, then you should produce labels instead of scores similar to MQM. So those are, I think, some of the, let's say, limitations when you're considering model-based evaluation metrics, and also like some considerations like using labels instead of score. And now, like right now, if we see, right, LLMs have been used as a judge for like many different tasks in NLP, right? And this is because of like very powerful, uh, strong base models such as ChatGPT or like GPT-4, right? To start with, suppose. So how well these models can do for evaluations, let's say in case of MT, right? So your paper title Gemba basically explores this. So what they do in this case is they prompt LLM with the source and candidate and ask it to generate like a direct score, like a direct assessment. And also they do it for MQM as well. And they find that the LLMs are also good at evaluating MT and can correlate well with human judgments as well. So this is one direction which is like right now taking up more shape, and like more work is expected to be done in like subsequent time in this area. And as your models keep on like let's say improving over the time, right? LLMs basically, they can be very good indicator for providing feedback on where the mistakes are, right? And these mistakes can be further, let's say, improved based on some additional augment, another chain of solutions, right? Not like, so for example, Palm models when prompted for MQM basically gave better annotations, like gave better correlation with the human annotations. Now let's take a look at different evaluation implementations, right? Frameworks that are there. So let's say if you want to evaluate any model of your choice, right? Like on string-based metrics, then the standard choice would be Blue. The one reason behind using like a standard framework, right, for string-based metrics is like all these metrics are more tokenizer dependent, right? So if you like, let's say, use a different tokenizer, right, then your correlation factor also changes, right? Basically, like the n-gram overlap with the reference, right? And the systems are not directly comparable. So Blue basically mitigates those by using a standardized tokenizer to basically, let's say, make sure that the results are consistent and comparable across different systems and also reproducible. Next is model-based metrics. So Comet and Blur all have their own packages, so which you can use directly out of the box. And those are, they support both. So like scoring with reference or without reference, and in both settings, so like Comet supports direct assessment as well as NPM. And there's some work like going on in Comet 2, which is work in progress, and you should expect like something out like probably by the end of this year or next year, early next year. So yeah, so and also one more thing, whenever you are performing metrics, basically for let's say evaluating your MT systems, you should always do significance testing in order to basically, let's say, reinforce the results that you got. And yeah, so that's probably for the automated evaluation. I think Pranjal will continue with human evaluations.
Yeah. Hello, can you stop, sir?
Yeah, he's already
Yes,
stopped.
Okay. So is the screen visible?
Yes, it is.
Yeah. So we kind of described right now the flaws of automated metrics, and so there is a need to conduct human evaluation as well to ensure that the results we have obtained are really good or really bad, or what sort of areas of improvement are there for our model. So human evaluation focuses on majorly two aspects: adequacy and fluency. Adequacy means how faithful is the translation to its source. Here the errors which are identified are omission or unwarranted additions or mistranslations. Here, to conduct a evaluation for adequacy, we need bilingual evaluators who are comfortable with both source as well as the target language. The second aspect which needs to be evaluated is fluency. So how fluent is the translation as a standalone sentence in the target language is what is evaluated in fluency. So factors like naturalness or grammatical or spelling errors are what are important when evaluating fluency. Fluency is evaluated by monolingual evaluators. But in general, in human evaluation, the most important aspect is inter-annotator agreement. So given that we conduct human evaluation across different persons or different set of people evaluated, and humans can, as we know, can be subjective. Some people can be much more lenient or some can be strict. So we want some sort of consistency to for the scores to be trustworthy. So enforcing consistency is an important aspect, which we'll discuss about as to how human evaluation is conducted and how can we enforce better inter-annotator agreement. Yeah. So a nice way of conducting human evaluation can be relative ranking, where annotators are shown outputs of two or more systems and they have to rank the systems. But the issue with this is it is a relative measure and it does not give any sort of absolute details as to how a particular system, how good or how bad is a particular system. It just gives you relative rank order of the systems. And usually it has been, literature shows that such a relative ranking based approach usually tends to have poor inter-annotator agreement. So usually a relative ranking is not much preferable, at least in the current setting. And there has been a lot of literature which says a direct assessment is better than having a relative rank. So let's get into direct assessment. Here, annotators have to rate for adequacy and fluency independently, and they have to provide a 0 to 100 rating. So annotators rate how adequately the candidate translation expresses the meaning of the corresponding reference translation. So you need reference as well as input as well. And fluency, in fluency, it is reference free, and the annotators have to rate how fluent is the generated translation as a in standalone text in the target. So this is on a scale of 0 to 100, and all systems are independently rated, and this is not a relative measure. So as the scores would be absolute and would be indicated indicative and mean something, and then we can understand which system ranks where and try to improve the system further. But so this figure summarizes the two approaches: relative ranking and direct assessment. In relative ranking, people have to just give their preference as to A is better than B or B is better than A. And in direct assessment, they are just given the output of one system at a time, and they have to assign a score of their, so from 0 to 100, what score is suitable for that translation is what is done in direct assessment. And finally, after getting ratings from different human evaluators, aggregation strategies might be to average the rating or take a max score. So we discussed relative ranking and DA assessment, but the problem with those as well as consistency. Given a score rating of 0 to 100 and without any guidelines in place, people might just give ratings of their choice, and that is not something which we would want. So here is where MQM would come to the rescue. Here we divide the error categories into accuracy, fluency, terminology, and there are 5 categories. And then in those subcategories, we categorize the type of errors like addition or mistranslation, omission are categorized under accuracy, and in fluency we have grammar, consistency, spelling. So these sort of this is already provided to the annotators, and then whenever they observe, so we will just get into example of a MQM annotation. So given a sentence and given the rating and error categorization in mind, they have to identify the errors as well as rate its severity, and then the final, and they also have to assign a final rating which takes into account the type of error and the severity of error as well. So having this sort of standardization or this characterization where the annotators have to actually identify the type of error as well as its severity, this sort of introduces much more standardization in the process. And in general, prior works have showed that MQM-based judgments are usually have good IA and are more reasonable or more informed judgments than just using direct assessment. So MQM is better, is the TLD. Another approach of so basically STS, which we had previously discussed, STS focuses on more on adequacy than fluency. So how equivalent are the two sentences is what we care about, as fluency might be subjective and depending upon use case. So in some use cases we prefer more informal style of text, more in some cases we prefer more formal style of text. So fluency might be subjective or varying depending upon the context, but adequacy is paramount, is what is the central idea behind STS. And this is the 6-point scale. 5 indicates the completely equivalent, 0 indicates completely dissimilar, and this is the rating strategy. And these following these guidelines, the annotators provide a 6-point rating for each of the systems independently, and then we rate the system based on their on these scores. But the problem with this STS as well, as we had also previously discussed, this people are annotators from different language teams and might not might not have their might have their own judgments, and some people are more strict or some people are more lenient. So it depends. So we need some sort of standardization. So cross-lingual STS or XSTS is the way of enforcing standardization, and the solution to it is calibration. So annotators are provided a calibration set. Usually this is English text, which the annotators have to rate for provide their ratings on, and using their scores on the calibration set, correction factor is determined, and this correction factor is then used to normalize their scores such that the scores are much more well calibrated, and the score ranges are much more consistency, and these so that these XSTS scores can be compared across languages. So this is the central idea behind a cross-lingual calibration. So in general, if you prefer more adequacy, more XSTS based evaluation is what you should do. Or if you are going for a direct assessment or versus MQM, MQM is what is preferred.
Okay. Where's the... Just 1 second. Let me present.
Share the screen.
Yeah, I'll share the screen. Just get to the future.
So we are pretty much close to the end of the tutorial. I'll be talking about the future because, although there has been quite a bit of work on related languages, massively multilingual machine translation that I've presented, related languages work is still rather new. Can you? Yeah. Related languages work is still not that much the focus of most of the community. And as we've already seen that related languages do have an implication for the quality of translation systems, we should definitely be giving them a lot more attention than we already give. So what is the niche that we can go into, right? So low resource performance can still be improved. This is an obvious thing. This is going to be something that no matter what we do, there'll always be a new low resource language. There'll always be new phenomena to improve on. Now, you might think that NLLB had 200 languages? But that's nothing. We have 2,000 languages in India. Okay? If you look at Latin America is a hotbed of extremely low resource languages. And if you're talking about such languages, I would say 90%, 99% of the languages are low resource. And even if you forget about resource, there's domains. You might have use domain data, but you don't have data for, let's say, another domain, like let's say biomedical and think about the implications for healthcare related machine translation. You go to travel to a country, you don't speak the language, having a high quality machine translation system, if it's a low resource language and it's a low resource domain, that's still a hot topic. That's still something that needs to be done. So we have a lot more opportunities to work on low resource languages and work on relatedness, how to transfer relatedness. Think about one thing, domain can be treated as language. Because if I'm a lawyer, I start speaking in the legal lingo. A person who speaks the same language, but a different lingo, let's say the person is a doctor, they might not understand all of the words that I'm saying. So domain can be treated as a language. If we have relatedness between languages that can be exploited, you have relatedness between domains that can be exploited. All of this information is transferable between the two different areas of research. Idiomatic usage is still something that MT models cannot handle. Okay, if you could ask the MT model to start translating an idiom, maybe ChatGPT can do it because ChatGPT has been trained on more or less the entire web. But if you design a special MT system, it can't handle idioms so well. So you have to be very careful about how to design good idiomatic translation MT systems. Non-English numerals expressed in words might result in hallucinations. So we have seen that for Indic trans, we have seen that for a few models, that instead of saying 5 in number, if you start saying, you put it in letters, sometimes there is some hallucination. Sometimes you want it in letters, but it starts giving the numbers and vice versa. It might make mistakes. That's something that needs to fix. There is dialects and languages. I'll get to that in a bit. There is speech translation, right? Now, more and more speech data is becoming available. Why do speech translation by speech to transcription followed by machine translation, where you can train something end to end? Now, Seamless M4T has kind of already made some strides in that. They have come up with a more or less end-to-end system that does speech-to-speech translation, where the actual work is speech to text and then text to speech, but everything is done in an integrated seamless style. So there is a lot of open questions, and speech translation in the case of related language is still something that I don't think has been explored in that much depth. So there is open opportunity over there. LLMs for MT, now that everybody's talking about LLMs, and we've seen that LLMs actually have good zero-shot performance, it's time to start thinking about how to boost these towards encoder-decoder quality so that one day, if possible, we have this unified framework. But I still doubt that you can actually beat encoder-decoder models. They'll always be the best for generation, in my personal opinion. Document level translation. Like, think about it. These MT systems, you don't use them to translate single sentences. Sometimes you want to translate entire web pages. Document level phenomena is still something that has not been handled. But how often can you say that you can have document level data for any arbitrary language? It's very hard. So if you can model document level translation and then transfer these capabilities to a related language, this is an important thing. It is also a case of distillation, if you ask me, because you can distill the ability, document handling capability of a high resource language to a related low resource language. Now let's bring in dialects, right? Not many of you know about this language called Marathi, but it's my native language. I speak about 3 dialects. These might sound unintelligible to most people, but to me, I know the clean difference between these dialects. And there are a total of 42 dialects just for this one language. And dialects sometimes end up being so unintelligible to another dialect, might as well be a different language. So right now, I'm already able to translate to Marathi, standard Marathi, to a certain level. But what about these 42 dialects? Still a hard problem. But if you see that vocabulary manipulation technique, right, where you start replacing vocabulary with noise, starting point for something. This is something, but again, you don't have data, you're not going to be able to do anything. So we have to start with data, and I'll come to that point as well. Think about dialects in Japan. I've lived in Japan for quite some time. Japan has a lot of dialects also. There is this one dialect called the Osaka dialect. There is a dialect for Kyoto dialect. Every prefecture has its own dialect. Most of these dialects somehow you can understand, but then there are dialects like Okinawan dialect. There is a Aomori dialect. Can't understand that stuff. It's Japanese, by the way, but it's a completely different dialect. So we have to be able to understand this dialectical problem and linguistic problem. Very rarely spoken languages also have their own dialects. How are you going to handle that? That is still an open question. So one other thing about dialects is when I go home and I talk to my mom, I don't always talk to her in standard Marathi. And sometimes instinctively the dialect kicks in. And most of the people who live, you go to a village area, everybody has smartphones, so everybody will have the need for machine translation to some degree to get some information. But if they can get information in their own dialects, that's a very nice thing we can do. And a dialect can be also a related language to a standard version of that dialect. So there is scope for relatedness even in dialectical translation. Now, Creoles is also one of the use case, and some dialects are spoken dialects. So Creoles, right? Mauritian Creole, there is stuff on the internet, but mostly people speak it. People don't write it down. Some people are embarrassed to speak their own dialects. Some people think that my dialect is, is like a village dialect. I will not use it. That is also another problem. So not only do we want to enhance dialectical translation, but we want to encourage people not to be ashamed of their local dialects, to be proud of these things. And that comprises most of the minor languages. So dialects that are only spoken, we can have scope for speech-to-speech translation. We'll have to figure out how to bring in these dialects in speech-to-speech translation. So let's collect data aggressively. That is one of the points. And you may have seen this, people who worked on language resources. You submit a paper to EMNLP, you submit a paper to StarCL. A lot of the reviewers sometimes tend to say like, oh, this is not worth ACL because it's a resource thing. Resources are the fundamentals of whatever research we are doing. So let's not look down on these kind of papers, especially the ones which look on low resource. So just to summarize, we started out with the big picture, which talked about the current state of machine translation. We went into data creation when we talked about manual data creation. What are the different considerations for data creation? What is the pipeline for curating high quality data, mining as well as automatic, as well as human? Then we went into modeling. We talked about vocabularies. We talked about scale. We talked about compactness, distillation, compression. And in this section, especially, we focused a lot on related languages. We talked about the mechanisms to boost transfer learning between related languages. Then we went into evaluation. We talked about automatic and human evaluation, the potential for transferring evaluation capabilities of learned metrics from one language to another. So we've seen that as well. So overall, I feel that this is just the beginning for work on related languages. If you look at the overwhelming amount of work that has not been focusing on the languages. If the ultimate MT model is going to contain all the languages of the earth, we have to make the case for how to exploit relatedness between languages and get to the best possible system. So with that, I'll end this tutorial and welcome questions if you have any. Yes.
Thank you for the nice tutorial. About the dialects, you are talking about many spoken dialects, but how many of them are written? Because you are focusing here on text-to-text machine translation.
Yes.
And I guess that there are not so many written dialects.
Yes.
Or that maybe every speaker knows the standard.
So I can answer that to a certain degree. When we were doing our work on Creoles, we found data for 28 Creoles. Not all Creoles are written. For example, Mauritian Creole is both written and spoken, but it's more overwhelmingly spoken than written. And yes, this tutorial is about like text-based translation, but most of the work is text-based. But when we talk about machine translation, it does not necessarily have to be text-based. I'm trying to motivate a more, let's say, longer term goal where we involve other modalities like speech as well as vision at some point of time. But yes, you're absolutely right. A vast majority of dialects are spoken. That being said, the native dialect, that one of the dialects of Marathi that I speak, most of the dialects somehow to some degree have data for religious texts, like Bibles. Even if they're mostly spoken languages, there will be Bible content written in that dialect. Even 99% of the time, people just speak it. So yes, there will always be a certain amount of seed data. And wouldn't it be nice if we can just use the Bible data to generalize to any other domain possible? Seems like a hard thing to do, but I don't know, that's a dream. So maybe I hope that answers your question. By the way, since we are in Indonesia, I can say that it's a hotbed of related languages also. There is so much of scope and there's a lot of good papers that have been coming out on Indonesian languages. So I'm really happy, that and these kind of works actually motivate the community in India also. I just wanted to put that out since we have researchers from Indonesia. I just really appreciate that. Yes.
More questions. Do you know about document level metrics?
Yes. So not as many as there should be, because the vast majority of the people use blue, and they have shown that blue does correlate to a certain degree. But when it comes to documents, it's not just the translation of the blue score that we should be caring about. We should be caring about document level phenomena. So there is anaphors, like are the anaphors being translated correctly? Are they being handled correctly? Ellipses and so on. So there is a paper by Elena Wojta on document level translation, and she has proposed data sets with different document level phenomena and how to evaluate them. In 2016, there used to be a shared task on pronouns. So what they would do is they would ignore the whole general machine translation quality, but they focus more on handling pronouns. Why? Because they are an essential part of anaphors that are usually presenting at the document level. Because when we write sentences, right, when we write an entire paragraph, we tend to use anaphors from time to time. When you say it has been used, you need to know what that it is in the previous sentence. So pronoun handling is one important case. How well have the pronouns been handled during document translation? So those kind of things. But yeah, we do need benchmarks, and a lot of benchmark data needs to be done.
So it's work of Wojta, it's a benchmark, but it's not a metric. So we kind of take text and
very hard to quantify. It's a very hard to quantify phenomena. Yeah. Sorry. So it's a very hard thing to quantify, as in how, if you ask me how well has a document been translated, it's very hard to say. And I'll elaborate on that more, because I have worked on structured document translation, where the important thing is to translate the XML tags, right? You have a web document, you have the hashtag, you have a variety of tags, and you want to make sure that if the word boy is encapsulated in the bold tag, when you translate it into Japanese, you want to make sure that the bold tag is around that translation and not some arbitrary word. So XML tag translation, when you evaluate, let's say, structured documents, you want to evaluate how well the structure has been transferred. So it cannot be just one number. It has to be a multitude of numbers which indicate the overall quality. And it's not necessary that there'll be top scores across all of these sub-metrics, but there might be some trade-offs that we are going to have to make. Choose one metric which is more important than the other. Yeah, anything else?
Can you elaborate what's comment DA and MQN?
So
how they different, what is better?
Sure. So when it came to comment DA, right, what happens is you give the human annotators the original source sentence, the translation, and the reference optionally, and they ask the translators to give a raw score. Just a score indicating how good they find this translation, good or bad. It's essentially like a continuous scale, but you ask them to give a number, anywhere between 0 to 10, typically it's between 0 to 25 or 0 to 100. It depends. But then comment, and this doesn't capture different phenomena. It doesn't tell us whether specific sub-phenomena like error types, grammatical factuality, and so on, have they been captured in the translation. So MQM was proposed by FlyTime in 2021, if my dates are correct. And what they did is they come up with criteria for annotation. They say dock 1 point if there is a severe grammatical error, dock half a point if so on and so on. By the way, these docking points is an analogy, but they have a criteria, and human annotators, they're asked to highlight specific parts and say what is wrong. Does this fall on what error category does this fall under? And then there is an equation based on the different things that they have highlighted. And from 25, you keep on deducting certain points till you get to a score, and that is known as the MQM score. So that is the key difference. Now, MQM scores are known to be more highly correlated with human annotations or human preferences as compared to essentially humans prefer MQM scores a lot more. And if you look at post-editing systems, right, if you look at any company, they want to know whether a particular sentence should be completely post-edited or rewritten from scratch, or should be partially edited. And knowing error categories allows you to make better decisions about whether something should be done from scratch, because now you have an explanation, you have a reason. One interesting point, we did have a slide on, let's say, LLM-based evaluation, right? Comment gives you a number, but you can prompt LLMs given certain MQM annotations, like given the sentence, given this translation, these are the kind of errors that are present. So therefore, for a tested sentence and a translation, can you tell me what the errors are? And LLM surprisingly can put out these MQM annotations. And that allows you to be more verbose, more detailed about what kind of evaluation you're doing. I hope that answers your question.
My last question or remark is that you said that related languages help,
Yes.
but from cosmetic experiments with implementation, the size of data also matter much
Yes.
more than related languages.
Yes, that is an important consideration. So that is something that we don't include in this presentation because we don't deny that size of the data doesn't matter, and size of the data typically does have some serious implications, as we've seen with ChatGPT, with GPT-3. Pump more data into it, things stop making sense. But at the scales that we typically work with, relatedness does have an impact, and we're zooming into that specific impact that relatedness has. But yes, with scales, some of the conclusions might be different. But overall, there is hard evidence over a number of papers that there is a certain impact of relatedness. There are more papers which show that relatedness matters than no. I hope that's okay. Yeah, you wanted to ask something?
Actually, I want to ask something.
Yeah, please.
And also the time is limited, but
Yeah, sure, no problem. Yeah,
So my question is, first of all, my name is Randy. I'm from Bandung Institute of Technology. My question is not specifically related to machine translation, but you said before about the about the prune and tune.
yes,
yeah.
yes.
So you told us previously that we can do the prune and tune, and we can find the most efficient model from the cycle.
Yes.
We prune and then we tune and do it all over again. So do we start from a model with fully connected neurons, and then we prune them gradually?
Yes, that is how it is.
Okay.
Yes.
So if that's the case, isn't that still a problem regarding the computational cost? Because we start from the fully connected neurons.
Yes. Yeah. So of course, this is so the whole concept of pruning and tuning is to get a more high quality but still sparse, like small size models for distribution. We don't really care about the training time at this moment. This is more about creating a deployable model. So of course, like you take a 54 billion parameter model, your first stage will have to be get rid of most of the experts and kind of convert it into a semi-dense model, and then start pruning and tuning till you end up getting rid of most of the parameters.
Okay, so the one that you explained before is the focus is more on the inferencing part.
Yes,
the
yes,
deployment.
the priority is for inferencing. Yes.
Okay, and my last question is, rather than we start from the fully dense connected neurons, can we start from sparsely connected neurons and add connection gradually?
That's the reverse of, let's say,
Yeah.
yes, I would say that why not, right? So suppose some company or some group, they only wanted to release the most efficient version of their model. They say, we are not going to release the whole dense model, which typically does not happen. You can always add new neurons, but it's the same as using adapters, isn't it? It's a kind of adding an adapter or a low rank adapter. I would say yes, in theory, yes, it's possible, but in practice, I would say that just use adapters. Don't add neurons, just use adapters.
Okay. Okay, thank you.
Okay, any last questions, comments? Okay.
So about the romanization or transferring languages into common script.
Yes.
And this, so do you have experience that the languages are spelled orthographically? Because in European languages or in Slavic languages, Czech and Polish, they can have different words, but there are some changes of the consonant, like we say H, and the Polish say G instead. So there are changes like this.
Right.
So it's not possible.
So Roman, okay, you know what? I did present work on romanization, but I'm a big critic of it. I think it is better to map to an orthographically similar or a consonant-wise, phoneme-wise similar language than to just map everything to English or to a common script blindly. You have to consider orthographic similarity. That's an important thing. Therefore, for Indian languages, Devanagari is a better map compared to English. because things become very complicated and transliteration becomes complicated depending on the language. I would say that romanization is the blind solution, but not the best solution. Okay, I think we are out of time. Thank you everybody for attending, and thanks to Jay and Pranjal. So just wanted to say that Jay and Pranjal worked really hard on making most of these sites, especially in the data creation part. Yeah, this has been something we are very happy to present. I hope everybody benefits in some way or the other. And yeah, thanks again for coming.
Oh no, absolutely no problem. Yeah, no problem, absolutely.
So you want to stand over here?
Yeah, sure.
Jay, Pranjal, could you maybe turn on your videos so that we can kind of
Maybe the other participants.
if anybody wants to have a commemorative photo.
Yeah.
Did Jay already run away?
Oh, that.
I have.
Okay, that's good. Pranjal, also please turn on your video. So you can click on the view and you can have a gallery view.
Yeah, okay. Gallery and then is it okay? Wait.
So everybody who has cameras, please turn them on if you're comfortable. If not, it's fine.
I've been keeping on.
So maybe everybody can stand over here. I'm short, so I can
Baby, how you
maybe you stand over there.
Okay.
You deserve more. Another airplane, another sunny place. I'm lucky I know. Let me go.
Are you also working on your
For the master, for my master now, I'm working on solving hallucination for language model instead of knowledge graph.
Okay, that's good.
But currently I'm still exploring this.
Ever think about doing
Like I said,
you can search for me on LinkedIn. I'll probably give you the mistake. So if you're able to find me, just
That's just not your dream. But
just reach out to me anytime, no problem.
Check WhatsApp.
So by the way, if you get the photo, just send it to you. How will you send the photos?
I will send it to him.
I'll try to contact you.
Thank you.
They shouldn't even know it was something here from.
I hope so. Everything is recorded. And you can always take a time. Thank you for coming. Thank you for taking the video. I will see.
Raj, maybe
I think
your code. Yeah.
guys, the session is done. You can leave. Thank you.
Thank you. Everyone.
They're waiting.
I'm so sorry about that. We already finished. Thank you. Okay, maybe you can end the Zoom
Yeah.
session also.
Okay.